black holes tearing apart enormous stars, pulsars spinning at incredible speeds and emitting powerful beams of energy, colorful nebulae with fireworks of newborn stars, galaxies of every possible color and size. All of these are found within our universe, but it's not infinite. It has a boundary, a literal wall, and beyond that, there's an absolute nothingness. Right now, we're going to make a journey to that wall. But first things first, our universe is like a humongous nesting doll. If you open it up, there's a smaller one inside. It's a galaxy. Inside that is an even smaller doll. That's our solar system. And the smallest doll of all is the Earth. Each of these dolls has boundaries that we're going to cross. For that, we'll need a spaceship, and a big one. It also has to be able to move 100 times faster than the speed of light. You get on board and start the engines. 62 miles above sea level is our first boundary. That's 10 times higher than passenger planes fly. This point is called the Kármán line. It separates the atmosphere of the Earth from outer space. Now we fly further to the edge of our solar system. We turn on the hyperdrives and fly past Mars, Jupiter, Saturn, Uranus, and Neptune. We've traveled a distance of 100 astronomical units. 1 AU is the distance from Earth to the Sun. And here's the boundary of our solar system, the heliosphere. Here, the speed of the solar wind decreases rapidly. First, it drops from 620,000 miles per hour to the speed of sound. Then, there's a layer called the heliopause. This is where the wind almost vanishes. And then, our ship experiences a bow wave. This is where we feel the force of the interstellar wind, which collides with the boundary of our solar system. When you pass this boundary, you find yourself in the dark of interstellar space. And here, you can find 2 human-made objects that made this trip for the first time in history. They're Voyager 1 and Voyager 2. Voyager 1 crossed that boundary in 2004. Voyager 2 did it in 2007. These space probes discovered that the heliosphere is not a perfect ball around the Sun. Its southern boundary is 10 AUs closer to the star than the northern one. So, we're moving in interstellar space and will soon approach a stone wall around our solar system. 200,000 AUs further, and there it is. This wall of rock is the Oort cloud. In fact, it's a pile of asteroids that surround our world. Scientists speculate that the Oort cloud could be the source of comets and meteorites that fall to Earth, but they're so sparse that we easily fly between them. Now we're in complete darkness. The Milky Way is about 106,000 light-years wide. In a conventional rocket, it would take billions of years to fly across that distance. But you throttle to the max. You masterfully fly past the stars and planets as if on a racetrack. And within minutes, you're at the edge of our galaxy. There's no more interstellar wind. All you see are bright dots somewhere in the distance. These dots are huge galaxies. We need to look at a map to make a route to the edge of our entire universe. You're here, near the Milky Way galaxy. It's part of a cluster of galaxies called the Laniakea supercluster. But even this huge thing is like a little street in a big city. Zooming out, we find Hydra Centaurus supercluster. Thousands of galaxies on the map look like little dots. Maximum zoom out. This is our entire observable universe. We thought it was infinite, but we may have proof that it has a boundary. It's here, 10 billion light-years away from our home. Even if you travel at the speed of light, a trip there would take twice as long as our whole planet has existed. During that time, the sun will either fade away or explode like a supernova, destroying our entire solar system. And if you can live that long and then return home, you will see that our galaxy is there no more. It's long since collided with the Andromeda Galaxy and merged into one big cosmic body. Luckily, your ship is able to warp space-time so that this journey will literally take a few seconds. Boom! Congratulations! You've arrived at your destination, the Eridanus supervoid. Some scientists believe this location is the evidence of collisions of our universe with something big enough to leave such a large scar. The Eridanus supervoid is an empty and cold space 1 billion light-years wide. If you think of this void as a cup, it would fit at least 10,000 galaxies, and it appeared after an accident of gigantic proportions. The object that crashed into our universe was Another universe! Yes, other universes may actually exist. Imagine that our entire universe is a huge bubble that contains all the clusters of galaxies in the observable universe. There could be an infinite number of such bubbles. They could have been born during the Big Bang. These universes may be different from ours. They may have other galaxies and nebulae. But these bubbles could also be parallel universes. This means that if you chose cereal over oatmeal in the morning, in another universe, your twin would choose the oatmeal. Every choice you ever made in life had completely different consequences in a parallel universe. And because the number of choices are infinite, there's a whole infinity of parallel universes. So, like a regular bubble, our universe has a wall that is near the Eridanus supervoid. Long ago, another bubble flew past ours. As they approached each other, their gravitational fields began to interact. Our boundary wall began to deform and pull toward the other universe. The same thing happened on the other side. Then the walls of our universes came into contact. But as these bubbles moved, their connection began to break, and the other universe just ripped a huge chunk of ours. A cold void was formed at the point of collision, and that was the Eridanus supervoid. The problem is that the universe looks the same to the observer, regardless of point of view. For example, imagine a basketball hanging in the air. Now, if we put an ant on the ball and tell it to find the edge of the ball, it will start running around it, making an infinite number of circles. But the landscape around the ant will not change. All it will see is a rounded horizon. That's because the ball remains the same from any point of view. The same thing happens to us when we try to find the edge of our universe, all because we imagine the world in three-dimensional space, and our view is limited. For example, you see an ordinary square in two-dimensional space, but if you add depth and change the point of view, voila, it's a cube. If we could see the universe in four-dimensional space, a square might be something completely different. But maybe we can leave our home bubble. The key to traveling to another universe might be inside a black hole. A black hole is one of the most mysterious objects in the universe. They're so heavy, they warp not only space, but time as well. It's like putting a heavy boulder on a net. The net will sag, and the closer you get to the boulder, the stronger the curvature is. Once you're in the gravitational field of a black hole, you can't leave it. We still don't know what might actually be in the heart of a black hole. Some scientists speculate that white holes also exist. Theoretically, they should be born along with black holes. Except for the color, they're the exact opposite of black holes. Nothing can come close to a white hole. At the moment, there's no data on such objects, but general relativity theory suggests they do exist. There's also a theory that a black hole may be a passage to another universe. When you get into a black hole, you can come out the other side through the event horizon of the white hole. So you bypass the boundary of the universes and find yourself in a completely different world. But we may have proof that a white hole exists. In 2006, scientists discovered an unusual burst of energy somewhere 1.6 billion light-years away from Earth. This burst was unique. It didn't look like a supernova explosion or even the merger of two black holes. Some astronomers believe it was the birth of a white hole. But because it was unstable, it was destroyed almost immediately. This process was reminiscent of the birth of our entire universe, the Big Bang. So, scientists called it the Little Bang. You're traveling through deep space, circling stars and entire galaxies. Whoa, looks like this multicolored nebula will soon collapse under its own weight and explode like a supernova. Now let's carefully circle this black hole. Try not to get caught in its gravitational field, or it'll swallow you like a space monster. Wait, what's that strange structure right there? It's a glowing wall. And if you look closely, each glowing dot is an entire galaxy. That wall has about 100,000 of these galaxies. The Milky Way has 100 billion stars. So this wall holds a quadrillion, that's 10 followed by 15 zeros, of stars like our sun. This giant structure is called the South Pole Wall. It's located about 500 million light-years from Earth. By comparison, the closest star to our home is Proxima Centauri, and it's about 4.2 light-years away. Rockets can cover that distance in about 73,000 years. So the journey to the South Pole Wall may take longer than our solar system exists. And this wall is simply gigantic, even on a cosmic scale. It's about 1.37 billion light-years long. To give you an idea of how large that is, the Milky Way is only 100,000 light-years wide. But you can't see this wall even with the most powerful telescope. The problem is that the Milky Way itself obstructs your view. It's so bright that it's hiding this wall. It's like trying to look at the starry sky in a metropolis. The light pollution won't let you do that. Scientists have been able to detect this galactic wall by measuring redshift. We know that all objects in the universe are moving. They spread out from each other as a result of the Big Bang, which happened billions of years ago. And when galaxies move, their light waves change slightly. By measuring this change, we can understand what the object is and how it moves. And this wall isn't even the largest in our universe. This is the Hercules Corona Borealis Great Wall. It's a giant flat superstructure about 10 billion light-years wide. That's around 10% of the entire observable universe. And it's also a wall. That is, a cluster of galaxies. We were able to detect this giant structure by gamma-ray bursts. It's the brightest electromagnetic event in the universe. You could even see it in the far reaches of our universe. Such bursts are a very rare event. In the Milky Way, for example, it happens once every few million years. If we notice many such bursts in a short time from the same place, it means that there are many objects like the Milky Way in that place. So, there are a lot of galaxies out there. Another unusual giant structure in the universe is the huge, large quasar group. It's about 4 billion light-years across. So, it takes a photon of light almost as long as our planet has existed just to get from one side of the structure to the other. And if you put the huge, large quasar group on the scale, it would be 6.1 billion times heavier than our Sun. Scientists have found that there are at least 73 quasars in that structure. These are some of the most unusual objects in the universe. They are the active cores of galaxies. At the center of a quasar is a supermassive black hole. This giant eats up the matter around it. A wild force of gravity twists the matter around the black hole, forming a disk. And this disk is the source of the strongest radiation out there. By comparison, the radiation from a single quasar is tens or hundreds of times stronger than that of all the stars in our galaxy put together. Because of such strong radiation, we can detect quasars, even at very long distances. That's why they're also called beacons of the universe. Scientists use quasars to study the universe and the movement within it. One of the most distant quasars from us is about 13.1 billion light-years away. This makes it one of the oldest objects in the universe. It appeared about 690 million years after the Big Bang, and it's almost 3 times older than our solar system. It's still glowing with extreme brightness, about 4 and 14 zeros times brighter than the Sun. Scientists explain that at the center of the giant is a supermassive black hole, 800 million times heavier than the Sun. All these giant structures are just building blocks of our universe. Look, this is our solar system. Now, zoom out a little, and this is where our home star is in the Milky Way galaxy. Zoom out again. Here's a local group of galaxies. All the bright spots here are galaxies. Here's Andromeda, and here's the Triangulum galaxy, plus a few dozen other slightly smaller galaxies. They're all gravitationally connected. The size of this structure is about 10 million light-years. That's 100 times the width of our galaxy. Zoom out, please. This one is the Virgo supercluster. It's 20 times larger than the local group. There are about 30,000 different galaxies, and the mass of the whole thing is about 1 in 15 zeros solar masses. Zoom out again. Laniakea. This structure is almost 3 times larger. It includes the Virgo supercluster and other smaller clusters. And there are about 100,000 galaxies here. It's not over yet. Zoom out one more time. Here's the Pisces-Cetus supercluster complex. This giant galactic structure contains about 60 clusters of galaxies. So there are more galaxies in it than grains of sand in the desert. You know what to do. Zoom out! Phew! This is the observable universe. There are over 500 billion galaxies. And the stars? Well, there are about 1 billion trillion stars. The observable universe has its own structure. Clusters of galaxies form chains and walls, as you've seen before. but these strands are separated by huge regions of absolute emptiness. These areas are called voids. In these places, there is no matter at all. There are fewer molecules in the voids than in an empty room. One of these voids has a very mystical reputation. It's the Eridanus supervoid, or the cold spot. It appeared here only 380,000 years after the Big Bang. It's almost 1 billion light-years wide and could hold hundreds or thousands of galaxies with trillions of stars. Some scientists believe that this cold spot may have been the result of the largest collision ever, a collision of universes. There's a theory that our universe is some kind of bubble, a huge sphere that contains all these walls and chains of galaxies. Now imagine that there's an infinite number of these bubbles. They could be parallel worlds or different universes. Many years ago, one bubble came close to the bubble of our universe. Their walls touched, and the two universes connected for a while. It's like two drops of water coming together. But that universe kept moving. The area where the bubbles joined became thinner and thinner until that connection broke, and the two bubbles detached from each other. At this point, the second universe ripped some of the material out of our bubble. All those galaxies that used to fill the Eridanus supervoid ended up in a parallel universe. Scientists supposed we might travel through other bubbles. Flying to the supposed wall of our universe would take forever, and then it would take even longer to fly through interuniversal space. So we have to use portals, or wormholes. Here's how it works. Imagine a piece of paper with point A on one side and point B on the other. Instead of moving all the way across the sheet of paper, we just fold the sheet so that point A is right above point B. All that's left to do is make a small hole, and the journey takes only moments. Some scientists believe that such shortcuts through universes lie inside black holes. But how do you survive falling into a black hole? You just have to pick one that's big enough. It's all about gravity. Imagine you're falling into a black hole right now. The closer you get to it, the stronger effect it has on you. It intensifies with every inch. At one point, the gravitational force that affects your head is much stronger than the one that affects your feet. Then you turn into spaghetti. Yum. But if you choose a supermassive black hole, like the ones at the centers of galaxies, the gravitational force in them increases gradually. They can be millions of times heavier than the sun and much bigger, but the gravitational force on your head and your feet will be almost equal, and you will still feel comfortable. Who knows? Maybe if you manage to survive a fall into such a massive black hole, you'd find yourself in a completely different universe where different laws of physics apply. But so far, this is just a theory.
There are a lot of unanswered questions in physics. How did universal energy and matter appear? Where did gravity come from? And much more. We've been trying for years to get answers to these questions. And one of the people who tried to do this was Paramahamsa Tiwari, the author of the so-called space vortex theory. What is this theory, and what does it say about the hidden laws of our universe? Let's figure it out. Paramahamsa Tiwari was the former executive director of the Nuclear Power Corporation, India. He took the space vortex theory, or SVT for short, first proposed by René Descartes and finalized it. He was always inspired by physics and its greats, even since his days as an electrical engineering student. After rigorous studies of the laws of physics, he discovered new equations defining matter and the mass and charge of the electron. After that, he came up with the SVT. This theory tried to explain the unexplained phenomena in physics, including the creation of the electron and gravitational, electrostatic, and electromagnetic energy fields, as well as other things. It also described the 6 hidden laws of the universe that underlie our entire world. But first of all, let's talk about the theory itself. Space vortex theory suggests that the universe is made up of vortices, or swirling patterns of energy. And according to SVT, these vortices are the fundamental building blocks of the universe. They're the driving force behind the laws of physics and the fundamental principles of our world. Basically, everything in the universe is connected and interconnected through these vortices. This theory isn't very based on any real observations, but rather on mathematical models and computational modeling. For example, some computational models showed how these vortices work in hydrodynamics and plasma physics. They showed that vortices in such systems can have a central point of attraction and can be interconnected. Other models were used to study how the energies inside the vortices move and how they can create different frequencies and vibrations. But some experts have criticized SVT for using only models and simulations. The biggest criticism is that this theory can't actually be tested. It relies on mathematics and not on some experimental data. That's why it's not accepted as a mainstream scientific theory. But it's still quite interesting and provides a unique perspective on the universe and our understanding of the laws of physics. For example, according to SVT, the universe has some underlying hidden rules that cause the creation of fundamental matter, their assembly, and movement. What are these laws and what do they say? Well, let's take a look at them. Law 1. The universe has only one primordial entity, space, i.e. absolute vacuum, that structures matter. This law states that space is the fundamental building block of the universe and that it's responsible for structuring matter. It suggests that space is the fundamental entity that creates and maintains the structure of matter, and that all matter in the universe is made up of the same fundamental particles, like electrons and positrons. Let's try to put it in simple words. Imagine that the universe is like a big Lego set. Just like how all the Lego bricks are made up of the same basic building blocks, the universe is made up of the same fundamental building blocks too. And these blocks are called electrons and positrons. But what holds these blocks together? Space, of course. Space gives it shape and structure, just like how the plastic container holds all the Lego bricks together in a set. So, the first law states that space is the fundamental building block that structures matter and holds everything together in the universe. Law 2. Matter is constituted with multiples of only one kind of fundamental particles, electrons and positrons. This law states that all matter in the universe is made up of the same fundamental particles, the electron and positron. These two are the Lego blocks we've talked about before. And, according to the second law, these tiny invisible particles make up everything, from a tiny atom to a giant galaxy. Just like no matter what the shape or size our Lego build is, it's still made up of the same building blocks. Law 3. The field distribution in space, as recognized by contemporary physics, linked with and emanating from matter, are effects arising from only one fundamental field in space. This law states that the fields recognized by contemporary physics, such as the electromagnetic and gravitational fields, are effects arising from a single fundamental field in space. It suggests that this fundamental field is responsible for creating everything that we observe in the universe. So let's try to put it simply. This time, imagine that the universe is like a big playground. All the different fields we observe, such as the gravitational and electromagnetic fields, are like different games we play in there. But no matter what we play, we're still in one fundamental space. This is the playground itself. It's the base that holds everything together. According to the third law, without the playground, we wouldn't be able to play any games. And without this fundamental field in space, we wouldn't be able to observe any fields in the universe. Law 4. There is no void in space anywhere in the whole universe except at the centers of the fundamental particles of matter, electrons and positrons. This law states that there's no truly empty space in the universe and that all space is filled with the fundamental field, the one we talked about before. It says that electrons and positrons can be found everywhere, and even the things we consider to be empty, like vacuum, are actually full of tiny particles. And according to this law, the only truly empty spaces we can find in the universe are at the centers of the fundamental particles, electrons and positrons. Law 5. From only one fundamental universal constant, all the constants considered universal in contemporary physics are derivable. This law states that all the constants considered universal in contemporary physics can be derived from a single fundamental universal constant. It suggests that all the constants in physics are interconnected and can be explained by a single fundamental principle. I know you've been doing a lot of imagining lately, but bear with me. This time, please imagine the universe as a big recipe. All the constants in physics, such as the speed of light, the gravitational constant, and the Planck constant, are like the ingredients. They're very different, and there are tons of them. But, just like how all the ingredients in a recipe are interconnected and come together to make one dish, all the constants in physics come together to make the universe. And, just like how a recipe has a main ingredient that holds everything together, physics also has a single fundamental constant that holds everything together. Law 6. The spatial structure of submicrocosmic fundamental matter is repetitive uniformly in the spatial structures of macrocosmic bodies like planets, stars, and galaxies. This law states that the structure of the fundamental particles that make up matter is repetitive and uniform across all scales, from subatomic particles to macrocosmic bodies like planets, stars, and galaxies. It suggests that the same fundamental principles govern the structure of matter at all scales. Let's go back to the analogy with the recipes and cooking. Using different ingredients and combining them in different ways, the chef can create new dishes. These will all be different dishes and they can be very simple or very complex. But when creating them, the chef still applies the same basic rules and knowledge they have, right? And just like that, the universe also creates different structures, from atoms to planets, stars, and galaxies. But it still uses the same fundamental principles to create all these things. So, this law suggests that the structure of the fundamental particles that make up matter is repetitive and uniform across all scales. These are the 6 fundamental laws of the universe according to the SVT, and even though it's not accepted by mainstream science, it's still a pretty interesting concept. There's this mysterious thing in space, an unusual spot that scientists haven't been able to explain for more than 15 years. There are different theories, and one of them says that maybe this is an imprint from a collision with a parallel universe. Is this true? Well, let's see. Take a look at this map. This is the map of our universe. Well, not really. This is actually the map of cosmic microwave background radiation, or simply CMB. Many, many billions of years ago, there was a Big Bang. It was so powerful that it created our entire universe. And, of course, such an event couldn't occur without leaving some consequences. And these consequences are literally everywhere. The Big Bang left electromagnetic radiation, which we know as CMB. We don't notice it in our daily lives, but it's literally here, under our noses. And if you had some kind of superhuman vision, you would see how everything around you shines with this dim light. This radiation is very important. If we hadn't discovered the CMB, we would never have found out about the Big Bang. Previously, scientists believed that the universe had always existed. There was no beginning and there was no end. It sounded pretty ridiculous to us now, but less than a century ago, people were absolutely sure of it. Stephen Hawking was one of the first scientists to guess that the universe did, in fact, have a beginning. The guy was so cool that he realized this as a student while working on his doctoral dissertation. But, unfortunately, he had no proof. If there was such a strong bang billions of years ago, then where are the traces? Where's the proof? Laughed people who believed in the eternal static universe theory. But don't worry, they had the proof rubbed in their faces real soon. In 1965, astronomers Arno Pienzas and Robert Wilson discovered CMB, and that was the first grandiose proof of the Big Bang. It turned out that radiation was everywhere. We just didn't notice it. In fact, at first, Pienzas and Wilson themselves mistook it for the noise of a big city, or pigeons, or something else. For their discovery, which turned the world of science upside down, they received the Nobel Prize. Alright, so people learned that they were surrounded by electromagnetic radiation. Then they started collecting more data about it. They accumulated more and more info over the years until they made this very map. This is a map of CMB temperatures. But while creating it, scientists discovered something unusual. Let's take a look at this map. It looks like a large and diverse pattern of cold and warm places. But in reality, our universe is quite uniform. All temperatures on this map are close to negative 455 degrees Fahrenheit with very little difference. All temperature fluctuations between these places are small, and each tiny speck actually spreads over millions of light years. So everything in our world is pretty calm and stable, except for one point. This cold spot right here. Astronomers first discovered it in 2004. First, it looked like nothing unusual. It's just a region where the temperature is below average for a couple of microkelvins. But remember, we're not talking about a small area. This is a giant cold region. It's literally billions of light years in size. Wait, the scientists thought, this can't be true. The universe should be consistent everywhere. According to our standard model, this cold spot simply shouldn't exist. But it does exist though. This isn't just some mathematical error, it's right there. So what is this cold spot, and how did it appear? Astronomers have been trying to find the answers to these questions for years. Even now, we have only a few theories. So let's discuss them all. Theory 1. Cosmic texture. This idea was brought up at the end of 2007. Then scientists suggested that this cold spot could be the hills of space. In other words, it may be a bumpy region of the universe, just part of its texture. But that's a silly explanation, so this theory was quickly discarded. Theory 2. The supervoid. This hypothesis was considered the most plausible for a while. It stated that the cold spot was actually the so-called supervoid. It's a terrifying, dark place of our universe with almost no galaxies. And because it's an empty region with almost no stuff in there, it seems cold to us. However, this theory was refuted in May 2017. After carefully examining the cold spot, scientists found out that there were no signs of a supervoid there. Moreover, voids and supervoids, which actually exist by the way, are still very small in size. The cold spot is literally thousands of times bigger than them, so there must be some other explanation. And there is one, perhaps the most bizarre of them all. Theory 3. A parallel universe. This controversial idea was put forward by cosmologist and theoretical physicist Laura Mersini-Houghton. She suggested that the cold spot could be an imprint from the collision of our universe with a parallel one. Standard cosmology cannot explain such a giant cosmic hole, says Mersini-Houghton. This is the unmistakable imprint of another universe beyond the edge of our own. Her assumption is based on the theory of the multiverse. This theory says that there's actually an infinite number of universes like ours in the world. They constantly collide with each other, giving each other a push which creates a new Big Bang. So maybe the cold spot is a bruise from such a collision. For quantum mechanics, such crazy theories are pretty common, but for standard physics and our simple understanding of the world, this is earth-shattering. Of course, we need strong evidence. And Mersini-Houghton's team has begun to work on it. Professor Tom Shanks from the Center for Extragalactic Astronomy at Durham University also participates in this research. The craziest sounding of the exotic models for the explanation of the cold spot, the multiverse is actually the most standard in terms of our current model of the universe, he wrote in one of his works. So, what evidence do we need? Well, our cold spot is located in the southern hemisphere. According to Shanks, if there really was a collision between two universes, we should find another cold spot, and it should be in the opposite northern hemisphere. If astronomers actually found it, this theory would be confirmed, and it'd become the first proof of the existence of a parallel universe. But it's not that easy. To find a second spot, we need the latest, highly sensitive telescopes. We also need to find out some info about the nature of dark energy, how it affects space, and, in other words, there's still a lot of work to do. Not so long ago, scientists actually believed they had discovered the second spot. Researchers from New Mexico thought they had found it in the northern hemisphere. But unfortunately, this is likely to be a mistake. The map these researchers used had a high measure of randomness, so it's possible that their discovery is just an accident caused by other voids. So basically, we haven't found another cold spot so far despite careful analysis. But again, even the best modern equipment is not perfect, and it doesn't mean that there's no second spot. It just means that we haven't found it yet. But if one day we did find it, it could change the world of science forever. We'd confirm not only the theory of parallel universes, but also the famous string theory. It could explain everything that occurs in our world. But if this happens, we'll get even more questions than we already have. How did these two universes collide? How does it all work? So far, it's all just guesswork. We can't claim that the cold spot is a print from the collision of parallel universes. But we can't refute this either. Actually, we may never know the truth at all. But it's still interesting to strive for it.
So, are you tired of boring old Earth? Want to know what lies beyond the starry night sky? You're not the only one. People have been asking the same question for centuries. Luckily, scientists have got you covered. They've discovered a lot of amazing places light years away from our blue planet. Just one light year is about 6 trillion miles. Mind-blowing, huh? So, hop on. The spaceship of knowledge is lifting off. Your first stop is 2.5 billion light years away from Earth. It's a quasar, one of the brightest objects in the universe and the first one to be discovered. A quasar isn't a star, but a distant galaxy. This extremely bright object gets its power from a supermassive black hole. A disk of matter swirls around the black hole and creates friction. It's kind of like when you're cold and rub your hands together to stay warm. The friction between the palms creates heat, making you feel nice and cozy. The same happens in the quasar, just the amount of heat is bigger, way bigger. I hope you remember to pack sunscreen lotion. The temperature at the heart of this quasar can reach 18 trillion degrees Fahrenheit. Also, there is light, a lot of it. This celestial object shines 100 times brighter than all the stars in its galaxy put together. Well, it's time to cool down a bit. Minus 457 degrees Fahrenheit, to be precise. This is the temperature of a young planetary nebula called the Boomerang Nebula. It sits 5,000 light-years away from Earth. NASA's Hubble telescope caught images of the formation in 1998. It's composed of gas coming from a star near the end of its life cycle. Inside the nebula, it's windier than in the Windy City. Winds reach speeds up to 310,000 miles per hour. And you gotta thank them for the nebula's chilling temperatures. Researchers were just impressed to find out that the temperature of the Boomerang Nebula is just 1 degree above absolute zero. 0 Kelvin should be the coldest temperature possible. This is the point where all molecular and atomic activity stops. Brr! Makes you want to crank up the thermostat in your spaceship. Next, you're going to a place you might not want to visit. Sorry. So, it's the most massive black hole. This giant is located at the heart of a large galaxy, some 10.4 billion light-years from our planet. Its mass is 66 billion times greater than that of the Sun. Enough to make our galaxy's supermassive black hole feel ashamed. It has a mass of merely 4.5 million times that of the Sun. But you better not get near any of them, as a black hole's diet consists of matter. By calculating how much matter they consume, scientists can determine their rate of expansion. And those black holes have quite an appetite. Astronomers believe there are stupendously large black holes, or slabs, hiding somewhere in the universe. If they're real, their mass is estimated to be greater than 100 billion times that of the Sun. Now, it's time to snack on something lighter. The spaceship enters the Kepler-51 system. It's home to the lightest planets in the known universe, called superpuffs. Sounds fluffy enough, and it is. These planets' mass is either the same or slightly greater than that of Earth. But this doesn't mean they're small. Think of them as giant cotton candies the size of Jupiter. They are newly born planets whose atmosphere is still cooling down. You might want to wait for this process to be over, though, as 500 degrees Fahrenheit is too hot to handle. But for experts, superpuffs are special. These planets are incredibly rare, as they've managed to discover less than 20 so far. Now, are you up for a race? Let's say the ship you're on is traveling at a speed of 25,000 miles per hour. This is the current human speed record. It was set by NASA's astronaut trio from the Apollo 10 mission in 1969. And no, I am not talking about Neil Armstrong and Buzz Aldrin. That was the Apollo 11 mission later that year. Right now, you're going to race against a star 18,000 light-years from Earth. Your biggest advantage is that this is a neutron star. It was formed when another massive star ran out of nuclear fuel and couldn't support itself anymore. Think of a car running on an empty tank. Victory couldn't be any closer, right? Well, not quite. When a massive star feels like its time is up, it shrinks and starts spinning. Figure skaters do the same during a spin. They fold in their arms to increase rotation to the maximum. This neutron star is the champion of the universe. It spins at a speed of 157 million miles per hour. That's roughly 27% of the speed of light. Whoa! Are you running low on energy at this point? Time to charge up from a gamma ray burst. Gamma rays are electromagnetic waves generated by various forms of radiation. These bursts were fairly unknown to science until the late 1960s. Satellites equipped with gamma-ray detectors accidentally recorded huge outbursts of radiation outside of our solar system. What were they? Nothing dark, definitely, as these are the most energetic forms of light. Scientists believe that gamma-ray bursts happen when two neutron stars collide and form a black hole. The other explanation is that they are in the final stage in the life of a supernova. This event happens when a star decides to go out with a bang. Gamma-ray bursts shine brighter than a diamond. They are 1,000,000 trillion times brighter than the sun. Talk about an energy boost. Your mood is lightened up by now. You want to visit a place that has a draw to it. No, it's not a beach resort, but a magnetar. It's a neutron star with a twist. Magnetars have a magnetic field that is 1,000,000,000,000 times stronger than that on our planet. But don't fall for their strong appeal. Let's just say you won't live to tell a tale if you get too close to one. In 2004, a flare that came off the surface of a magnetar managed to compress Earth's magnetic field from a distance of 50,000 light-years. Quite impressive for a star the size of a city. Makes you wish to team up with this oversized magnet to commit the greatest heist ever. A magnetar has the ability to swipe all the credit cards on planet Earth from a distance halfway to the moon. Luckily for humans, NASA has discovered only 31 of these stars so far. You have barely escaped the pull of a magnetar. Suddenly, you start to sense a strange force drawing you away from your home base. It is the Great Attractor, one of the biggest mysteries of the universe. This massive gravitational irregularity has been pulling us closer and closer to it for billions of years. Scientists estimate that the Great Attractor is located at the center of the Laniakea supercluster. The name means immeasurable heaven in Hawaiian. It represents a gigantic collection of planets, stars, and asteroids. Our home galaxy, the Milky Way, is just a speck in this enormous supercluster. According to the Big Bang Theory, not the TV show, the real theory, the universe has been expanding in all directions. But the mysterious Great Attractor is slowing things down. How exactly? Researchers still need to figure this one out. On the bright side, they are good at naming things. The end of the universe would be called the Big Crunch, if there's anyone left to call it that. Your journey, too, ends at the edge of the universe. The most distant galaxy from Earth is the oldest one as well. The galaxies that formed first after the Big Bang have drifted the furthest. So every time advanced telescopes detect a far, far away dot, they give scientists an image of the origins of the universe. This is our home planet Earth and its satellite, the Moon. Zooming out, and here's our solar system. A bit more, the Milky Way galaxy. And we're a small dot among an infinite number of stars. Now, even farther out, a cluster of galaxies, dots and swirls in the endless space. Further, there's Laniakea supercluster. That little dot here is our galaxy. Moving on, Hydra Centaurus supercluster. Huge clusters comprising thousands of galaxies are no more than a speck from here. Next, Pavo Indus supercluster. This is an area 200 million light-years wide. We can zoom out until we see the entire observable universe. Each little dot in here actually contains thousands of galaxies and quadrillion stars. Scientists speculate that our universe may look like a bubble, and that bubble might collide with another universe. Yes, other universes could exist. Actually, even a whole infinite number of those. All of them could have appeared after the Big Bang. The collision between them isn't impossible either. At least, it might have happened before. And the proof is here, in the direction of the constellation Eurytinus. This place is called Eurytinus Supervoid. It's about 1 billion light-years wide. By comparison, the width of our entire galaxy is only about 100,000 light-years. There's absolutely nothing in this place, and it may be a trace from an old collision between our universe and another. Scientists think they were passing by each other. When the distance between them was minimal, the gravitational forces of the bubbles began to pull toward each other, just like two drops of water trying to connect when they're close. But the speed of the universes was too high for them to continue interacting. So the other universe just tore out a piece of our bubble. There might have been about 10,000 galaxies in that void, and all of them were either destroyed or taken over by the other universe. Let's travel to the edge of our universe to see how this collision might have taken place. We're 10 billion light-years away from our home. Here, in another galaxy, we see amazing nebulae of different colors and shapes. And if you look in the other direction, there's a huge wall moving at us. All these bright sparks on it are enormous galaxies about to collide with us. But in fact, it's a humongous mirror that only reflects our universe. Here, space-time is distorted and begins to be pulled into another universe at a tremendous speed. The usual law of physics may simply stop working at this point. Gravity may disappear, and with it, all the stars would explode, and people on the surface of planets would hang in weightlessness. But if the universes didn't go at a tangent but crashed directly into each other, things would be much scarier. The enormous amount of collision energy would probably cause an incredible explosion. Its force would simply destroy everything in our bubbles. Still, the two bubbles might begin to merge too. At first, all galaxies at the edge of the universes would be torn apart, but then the merger would begin. The galaxies would start moving chaotically. They would fly past each other, break apart, collide, and explode. The collision of two galaxies is an accident of enormous proportions, and it might happen to our home quite soon, in space terms. The Andromeda Galaxy is heading our way. It's a spiral galaxy about twice the size of ours, and there are about 1 trillion stars there, which is twice more than in our Milky Way. At the very center of this bright galaxy lurks a dark beast, a black hole. Its weight is 2 8/8 of the Sun's mass. Red giants hundreds of times larger than our Sun. Pulsars emitting enormous amount of energy like spotlights. Rogue stars, and many large and small black holes. This soup of dangerous objects is moving toward us at 68 miles per second. A trip to New York to Los Angeles at that speed would only take half a minute. The disk of Andromeda can already be seen with the unaided eye on moonless nights. As time goes on, it'll get even bigger. As Andromeda gets closer to us, its gravitational force will begin to stretch the arms of our spiral galaxy. It'll begin to unwind. The stars and planets will lose their orbits. One possible scenario is that an unknown asteroid, or even a dwarf planet from the Andromeda Galaxy, will crash into the Earth at an incredible speed. Our planet will explode just like a balloon from this impact. Oh, goody. Another option involves stellar collisions. Our sun would face another star. The bigger star will slowly begin to consume the smaller one. First, it will steal the light upper layers from it, and then it will eat it just like spaghetti, or even like rigatoni. When a large star reaches its critical weight, it will burst. This explosion will destroy everything around it, including our solar system. Perhaps the shockwave will even reach other neighboring stars. Yet another scenario is that our solar system will be thrown into dark space. Imagine a tennis ball tied to a rope. You take the rope and spin the ball over your head like a sling. Then you let go of the rope and send the ball flying. This is what will happen to the Sun and all the planets around it. We'll find ourselves in dark and cold space. But life on Earth will not be affected. We'll still have our bright star to keep us warm. The only disadvantage is that all the stars in our night sky will disappear. And the most likely possibility is that the merger of two giant galaxies will have no effect on us at all. The thing is, the distance between stars and planets in space is enormous, so they can all just mix together and form one giant cloud. It would be like shoveling fine sand through a big sieve. The objects won't interact with each other. But the most interesting thing will happen to the black holes in the centers of our galaxies. Right now, there's a dense cluster of stardust and stars around them. As Andromeda and the Milky Way come closer together, they will begin to dance with each other. Gee, will it be the twist or the foxtrot? And when the black holes get close together, they'll begin to swallow all matter around one another. Billions of tons of colored stardust, asteroids, and star particles will fly toward the very center of either black hole. It might seem like this process happens very slowly, but it's an illusion. Super heavy objects like black holes warp the space-time grid, so time is much slower near black holes. And all objects that seemingly stay on the event horizon for weeks or even months are actually long gone. When the black holes finally come together, they merge into one supergiant black hole, but its mass is slightly less than the combined mass of the two dark monsters. Some of their weight is transformed into collision energy. This energy is released so strongly that its waves can be felt in other galaxies. Now, a huge black hole gathers all this dense and hot core of the two galaxies around itself. At some point, the black hole feels full and throws out powerful jets of energy into space. This is called an active galactic nucleus. It's one of the brightest phenomena in the universe and the most powerful source of electromagnetic radiation ever known. These jets may be more than 5,000 light-years long. By comparison, the distance from Earth to the nearest star, Proxima Centauri, is only 4.2 light-years. And the explosion that accompanies the jets has the power of 100 supernova explosions. Wow, blows my mind. The blast wave from this event could even reach the edges of a new galaxy, and this outburst would be visible from millions of light-years away. Now, there are dense clouds of multicolored dust at the center of merged galaxies. The weight of these clouds is so great that they begin to shrink and take on a round shape. Gradually, they become so heavy that they compress the core and nuclear reactions start inside them. The temperature begins to rise and soon, boom, there's a supernova. It's a veritable fireworks show at the center of the galaxies. Stars erupt from the fog and form new hot worlds. At this point, the arms of the two galaxies that were previously pulled out slowly return to their former shape. The super-heavy center of our galaxy has such a gravitational force that it affects stars and nebula hundreds of thousands of light-years away. The galaxy's arms twist again, and we see the new and finished galaxy, the Milkomeda, or Milkdromeda. Hey, how about the Milky Way? Blah blah blah. Well, that's hard to say.
13.8 billion years ago, a mysterious explosion happened in space. It was chaos, a time when the stars, planets, asteroids, the rest of the space bodies, and galaxies were born. It was the Big Bang, a theory we all know about. But no one knows for sure what happened, where the universe came from, and what was there before. Some even think the universe went through a cycle where it contracted and expanded several times. In 1991, a cosmologist from Stanford University named Andre Linde had submitted an article with the main idea that there was a possibility the universe had been created in a laboratory. His theory said there was a chance an advanced civilization somewhere out there had created our universe. This civilization has made an entirely new cosmos that later evolved its own planets, stars, and intelligent forms of life. 30 years later, many scientists take this theory pretty seriously. They even started talking about things that we, as a civilization, can do to get to such an advanced level. The theory says this advanced civilization decided to add technology that helped to create a new universe out of nothing. It happened through quantum tunneling. It's when an atom can appear on the opposite side of some barrier, even though it's supposed to be impossible, considering the laws of physics of our world. Like if you wanted to pass a tall wall, but you can't pass it with ladders or go around somewhere. Imagine you can just walk through it like a ghost. In our world, it's not possible, but a more advanced civilization perhaps can do it. Plus, they realized how they could create new universes. Right now, on the cosmic scale, we could be a Class C civilization. We don't know how to recreate some things. For example, conditions on the Earth for when our central star, the Sun, goes out. If we manage to become a Class B civilization, we'll learn to adjust conditions to be independent of the Sun. That means we might be able to learn how to live even without it. And if we level up and become Class A, we'll know how to recreate cosmic conditions and produce our own cosmos in our laboratories. We think of the world we live in through 3 dimensions of space: east-west, north-south, and up-down. There's also 1 dimension of time, which means we can distinguish past from future. A 5th dimension would represent 1 more extra dimension of space. The theory of its existence was first mentioned in the 1920s. It was inspired by the theory of gravity by Albert Einstein, who said space-time is warped by matter and energy. We can't perceive these 4 dimensions, but we see how an object moves and attribute it to gravity. And maybe there's some other force, like the electromagnetic force, that's more than 1,000 times stronger than gravity, that could explain things going on in that extra dimension of space. The 5th dimension is curved in a way we can't see it, but the idea about it was mentioned in a string theory. It considers the universe as really small strings of mass energy, not as particles. They vibrate in 10-dimensional space-time, considering 6 dimensions are rolled up way smaller than a single atom. That led to the picture of the universe as a 3D island that floats in 10-dimensional space-time. Also, the 5th dimension might be an excellent explanation to tell us more about dark matter. That's the invisible stuff with a mass, but we can't see it, nor can it interact with ordinary matter. And dark matter is 85% of all the matter in our universe. The universe can't be still. It's constantly in motion, either contracting or expanding. We used to think there were 100 billion galaxies, but it turns out there are more than 1 trillion. The galaxies are moving away from each other. This is what it means when scientists say the universe is expanding all the time. There are voids between galaxies that sometimes stretch millions and millions of light years across. They can seem empty, but they can also contain way more matter than we can find in galaxies. Still, stars usually can't be formed there because the matter between those areas has lower density. But there are still plenty of so-called intergalactic stars. A good example is the Virgo galaxy cluster, 10% of which are intergalactic stars. We don't know how exactly they got there, but there are 2 possible ways. 1. Stars can collide, merge, or pass close to another galaxy, which can kick it off from its parent galaxy. Option number 2. A supermassive black hole can accelerate a star to very high velocities if they have a close encounter, which can, again, make a star be expelled from its parent galaxy. If you could have a giant magnet, you could even pull something out from the vicinity of a black hole. That's possible if the magnetic field near a supermassive black hole is as strong as the black hole's gravitational field. But it doesn't work if we're talking about material that's already beyond the black hole's event horizon. That's a spot with a gravitational force so powerful, not even light can get away. You'd need to accelerate this material to the speed of light, at least, to get away. For that, you'd need an infinite amount of energy. But A magnet could help if something's heading toward the black hole but didn't get inside yet. When someone mentions a black hole, you might get a picture of some giant void in space. But the Milky Way is most likely full of thousands of smaller black holes that float around the galaxy. When a star comes to its end, it will destroy itself in a supernova explosion, which is a cataclysm of energy. In that explosion, the densities in the core will reach an intense enough state that nothing will be able to escape. At the same time, the major part of the star explodes outward, but a part of it collapses inward, creating a black hole. The bigger the star, the bigger the hole. The black hole then swallows everything that comes in its way, including other stars as well. When a star gets sucked up into the black hole, it's ripped apart because of the strong gravity inside the black hole. Some of its parts fall into the black hole, while others get ejected at incredibly high speeds. Some black holes might have been formed in a different way. The early stages of our universe were, to say the least, pretty chaotic. It had high temperatures and pressures, and was in a state that shaped the entire cosmos. Under the right conditions, any old gas patch may have shrunk itself to become a black hole. And they came in many different sizes, from something that weighs a couple of pounds to giant masses like thousands of suns, and those in between. They aren't really black. Black holes are areas with strong gravity, and no object can escape when it gets inside. They feed off electromagnetic radiation, such as light and space particles. Since they're consuming matter all the time, black holes give off a dark glow. The Earth is not that close to the inhospitable edge of the solar system. We're the sixth planet from it. Scientists made a pretty cool 3D map of our solar system, where we can see what the edge looks like. It took them 13 years to design it. The boundary is called the outer heliosphere. It marks the area in space where the solar wind, which is the stream of charged particles our sun emits, gets deflected and draped back by the radiation coming from the empty region beyond our solar system. The inner layer of the heliosphere is where the sun and the planets have a rough shape of a sphere, while the outer layer is not that symmetrical. This asymmetry happens because our sun is moving through the galaxy and goes through friction with the radiation in front of it.
Bang. That's how it all started, around 13.8 billion years ago, and was figured out over the past 100 years. Everything we see in space today, planets, asteroids, comets, stars, it wasn't there at the beginning. In the 1920s, astronomers came up with the idea of how a long time ago, the universe was just a single point, an extremely hot, like trillions of degrees hot, compact, dense point that stretched and expanded unimaginably fast. Matter that started flying in all directions at the speed of light at one particular moment. The Big Bang was complete chaos, with teeny tiny particles that were mixed with energy and light. Yes, a total mess, but still, in the first minute after the Big Bang, the base for everything that would later appear was almost finished. It was hot only during this huge blast. As soon as the expansion started, the universe began to cool down, similar to when gas cools when you spray it from an aerosol can. During that process, part of the energy kind of froze out, just like the water freezes into ice. Here, pure energy got frozen and solidified into matter. 1 minute after the bang, the cooling thing was still going on, extremely fast and literally everywhere at once, since the universe really doesn't have edges. It wasn't just a compact dot anymore. The base for further expansion and all that's coming was being formed. Remember those tiny particles from that first boom stage of the universe? They started grouping together, which formed atoms of helium and hydrogen. It took about 3 minutes for most of the helium and all of the hydrogen in space to be made. These two are the most common elements and the basic materials that later formed the first galaxies and stars. Just because the base wasn't finished doesn't mean the creation of the universe stopped after those first couple of minutes. True, after that, no new elements were created for millions of years, which is why the initial version of the universe was entirely helium, hydrogen, and energy. But eventually, atoms began to slowly group together, which, after lots and lots of time, caused the creation of galaxies and stars. Clouds of helium and hydrogen grouped and turned into stars that had gravitational forces. Our Sun is also made of 3/4 hydrogen, while the rest is helium. 1/4? Yeah. At later stages, some other, heavier elements started to show up too, such as carbon, iron, oxygen, and so on. It wasn't all about chemical processes where new elements, stars, or planets kept coming. The whole universe has been expanding ever since the Big Bang. Researchers realized other galaxies are kind of moving away from ours. Guys, you need to stop doing that. How will we discover alien life out there if you keep running away all the time? And not just that. The farthest galaxies are actually moving quicker than the ones closer to our galaxy, the Milky Way. The universe is fabulous, unknown, mysterious, scary, and completely silent. Imagine yourself floating in your spacesuit somewhere above Earth. All you could actually hear is the sound of your own breathing, nothing from out there. Since there's no atmosphere, sound doesn't have a way to travel or be heard. Speaking of spacesuit, that thing costs around $12 million. I guess that means we'll have to wait up a little bit more to try that whole chilling in space thing. Mercury is the closest planet to the Sun, so you might think it's the hottest one too. And yet, Venus actually takes the title of the hottest planet in our solar system, with the surface baked by a temperature of 840 degrees Fahrenheit. Fair enough. Mercury doesn't have an atmosphere, which is in charge of regulating temperature, so it loses the race for the title of the hottie of the solar system. Venus also has pretty long days. Just one takes around 243 Earth days. Now that comes in handy for those people with pretty long to-do lists, who like to take it easy and slow. However, Venus orbits the Sun in 225 Earth days, which means 1 year there lasts 18 days less than a Venus day. You can have 2 birthdays in 1 day then? Well, 2 birthdays in a day could be one of the good sides, but the downside is that on Venus, it rains sulfuric acid and snows metal. Not so fun anymore, huh? The Earth is cool itself. Being 4.5 billion years old and the only known planet that supports life, it also has more trees than there are stars in the Milky Way. 3 trillion, while there are only 100 to 400 billion stars. We may have counted trees, but still, so little do we know about our ocean. Only 5% of it is explored, so we know less about it than about Mars or the Moon, whose surfaces have been fully mapped. It's funny how outer space is just 62 miles away from us, counting from above sea level on our planet. Seems so close, I sometimes go that distance just to have my breakfast. And yet, only 5% of the universe is visible from Earth. 68% of it is dark energy, while 27% is dark matter, which we can't see with a telescope. So close, yet so far. We will always see the same side of the Moon, no matter where we are on Earth. The Moon rotates on its axis at the same speed it orbits the Earth. This is called synchronous rotation. Sunsets on Mars are blue. That happens because the fine dust on the red planet has the size perfect for blue light to efficiently penetrate the atmosphere of Mars. So the blue light scatters, after which it stays closer to the direction the Sun goes, unlike the light of other colors. The universe is full of wonders, and one of them is a planet made of diamonds. Yay! It's twice bigger than the Earth, and scientists believe it's mostly covered in diamond and graphite. Now to get there, you might probably need that $12 million spacesuit, together with a really expensive ship. But if, and that's the key word here, you manage to go there and back, you may even easily pay it off. Scientists also have some predictions as to the end of everything. Oh boy, ready for this? At its early stages, the whole universe was dense and compact, so it was really thick. But after around 400,000 years, it kept expanding, which made it more transparent. All of this encouraged releasing light we know today as the cosmic microwave background, or CMB. It's like if you turn your TV on an empty channel and switch off the cable, you'll see the static black and white dots moving on your screen. There's something like the CMB, and also an afterglow of all that energy that was released during the Big Bang. CMB is still here. Astronomers can see it through the microwave telescope. Expanding never actually stopped. The universe is still spreading every second at an unbelievable speed, causing all the objects in space to move away from each other all the time. How repelling! We know it because the Sun from other galaxies appears redder than it's supposed to be. This is called redshift, and it happens when the source of light moves further from the one who's observing it. Then there's gravity. It attracts all objects in the universe to each other, which is the reason why planets keep orbiting the Sun or why our solar system orbits the center of the Milky Way. It's why we stay on the ground, while in space we'd float since there's no gravity up there. Having all this in mind, scientists got the idea that one day the universe will simply take the opposite direction and start shrinking back, which will be known as the Big Crunch. Whether this really happens depends on the type of our universe. If it's open, it'll keep expanding and nothing will ever stop it. But over time, as it's stretching, the density will become so low, galaxies won't be able to form new stars, and the existing ones will fade away. When space loses all the light and heat, life won't be possible. The universe will just remain as a cold beyond, which will keep spreading thinly into endless darkness. And then, Big Crunch or not, bang! It all disappears. Hey, good thing we have billions of years ahead of us, huh? Well, maybe you. I won't be around then. I'm going to retire.
A recent study suggests the universe is similar to your brain, only at a much, much larger scale. The brain's neural network contains about 86 billion neurons. The observable universe has at least 100 billion galaxies. Both galaxies and neurons have a similar structure. It's a complex web of nodes linking up long thread-like fibers. But in each of these systems, the fibers make up a mere 30% of the total mass, and the remaining 70% are either water in the brain or dark energy in the universe. The ways that galaxies and webs of neurons connect with one another are surprisingly similar. In both cases, the process follows the same physical principles. At the same time, some researchers claim the resemblance between the brain and the universe is only superficial. Your mind perceives tiny details and joins them, and then it comes up with a conclusion that has nothing in common with reality, like the brain is a mini-universe. In billions of years, the universe is likely to expand so much that we won't be able to see any stars in the sky. To turn Earth into a black hole, you'd have to squeeze it until it was the size of a marble. And if you wanted the sun to become a black hole, you'd have to compress it until it's no more than 4 miles across. A starburst galaxy is a galaxy that's forming tons of new stars at breakneck speed. It usually happens after 2 galaxies merge into one. While Earth has only one natural satellite, Jupiter is surrounded by at least 79 moons. In the universe, there are not only dwarf planets, but also dwarf galaxies. They have from 1,000 to a few billion stars. For comparison, the Milky Way galaxy is made up of 250 to 400 billion stars. A supermassive black hole 250 million light-years away from Earth hums the deepest sound ever detected from any object in the universe. It's 1 quadrillion, which is 1 with 15 zeros, times deeper than what the human ear can hear. Planet Kelt 9b is 670 light-years away from Earth. It's an ultra-hot Jupiter. Those are giant, scorching hot planets with a mass similar to that of Jupiter. On Kelt 9b, the heat is so great on the day side of the planet, it tears molecules apart. Any liquid floating in outer space forms itself into a sphere. It also happens in low Earth orbit. Our home Milky Way galaxy is more than 105,000 light-years across. All the planets of the solar system would fit between Earth and the Moon, with some space to spare. Black holes spaghettify things. It happens when something gets past the point of no return. Then the black hole's gravitational pull starts to stretch this object in one direction and squeeze in another. The first celestial body that astronomers identified as a spiral was the Whirlpool Galaxy. Its long arms are made of gas and stars, and everything is sprinkled with fine space dust. When you're on Earth, you can only see 5% of the universe. A star coming too close to a black hole can be torn apart by its gravitational force. WASP-12b is a giant planet 1,400 light-years away from Earth. It's made up mostly of gas. Unfortunately, the planet is doomed. It orbits too close to its parent star. In about 10 million years, WASP-12b will be swallowed by its greedy sun. Our Milky Way galaxy and the Andromeda Galaxy, its closest neighbor, are going to meet in a bit less than 4 billion years. When they collide, they'll form one huge elliptical galaxy. One of Saturn's smaller moons, Enceladus, reflects almost 90% of the sun's light. It makes the moon one of the brightest objects in the solar system. But since it reflects sunlight instead of absorbing it, the temperatures on Enceladus's icy surface drop to -330 degrees Fahrenheit. The highest mountain in the solar system is Olympus Mons on Mars. It's 3 times as high as Mount Everest. If you were standing on top of Olympus Mons, its slopes would be hidden by the planet's curvature. In our solar system, Mercury and Venus are the only 2 planets without moons. Scientists who are planning to send droids to Mars want to load the machines with lots of heavy equipment. The droids will also be built from stronger materials, all because of the relatively low gravity on the red planet. Everything on Mars is almost 3 times lighter than on Earth. Pluto's largest moon is half the size of the dwarf planet itself. This makes Charon, that's the moon's name, the largest known satellite relative to its parent size. There are 3 golf balls on the moon. They were launched during the Apollo 14 mission. Mathematicians claim white holes might exist, even though scientists haven't found one yet. If you came across a white hole, you wouldn't be able to enter it from the outside, but you'd see light and matter escaping from within. On our planet, one full rotation takes 1 day, but the sun is so enormous that it needs 25 to 35 Earth days to make one rotation. The moon is not a perfect sphere. It's shaped more like an egg because of the Earth's gravity. Spacesuits protect astronauts from huge temperature differences during spacewalks, from -250 degrees Fahrenheit to +250 degrees Fahrenheit. A neutron star gets born after a supernova collapses. After birth, it rotates extremely fast, about 60 times per second. But this rate can sometimes grow up to 600 times per second. In 2007, astronomers started to receive ultra-bright and ultra-strong radio signals. Named fast radio bursts, they were coming from somewhere billions of light years away. When astronauts are in space, they often see random flashes of light. They occur when cosmic rays hit the optic nerve in the eye. If you traveled around Pluto's equator, it would be the same distance as walking from Rome to New York City. If you visited GJ 504b, a planet located a mere 57 light-years away from Earth, you'd see that the planet is glowing. It's because of the heat left after its formation. The planet's color is a dull magenta, like a dark cherry blossom. Jupiter has the shortest day of all the planets in the solar system. It lasts just 9 hours and 55 minutes. Because of its fast rotation, Jupiter isn't a perfect sphere. It's a bit flattened. Venus has more volcanoes than any other planet in the solar system. There are at least 1,600 of them on the planet's surface, but most of them are extinct. Mercury has wrinkles. When its iron core was cooling, the planet's crust contracted. It made the surface of the planet uneven. Nuclear pasta found inside neutron stars is believed to be the strongest substance in the universe. These noodles of neutrons can be 10 billion times stronger than steel. Some astronomers believe black holes might have no event horizon, aka the point of no return. Instead, there might be the apparent horizon. It can only trap stuff for some time. Later, matter or energy escapes, but in a different form. Each Apollo mission needed 15 spacesuits. Each member of the three-person main crew needed 3 suits. One was for training, the second for flight. And there was also a backup suit, in case something went wrong with the flight suit. And each of the 3 members of the backup crew had 2 spacesuits, one for training and one for flight. Scientists believe Mercury might still have a partially molten core. It could explain why the planet has a magnetic field, even if it's just 1% as strong as Earth's. Dust storms on Mars are the most severe in the whole solar system. They can be raging for months on end. On planet Kepler 16b, which is 245 light-years away from Earth, not one, but 2 suns set over the horizon. The planet is as massive as our Saturn, but has a higher density. It takes 45 minutes to put on a spacesuit. After it's done, an astronaut needs another hour to adapt to new conditions. Earth-grazing fireballs are bright meteors that enter the Earth's atmosphere, but then leave it again. Triton, one of Neptune's moons, orbits the planet backward. It's the only big moon of any known planet to do so. Triton is also gradually getting closer to Neptune. Experts think that, eventually, the moon will be pulled apart by Neptune's gravity, and then it'll form a ring around the gas giant. Dwarf planet Haumea, which is further from Earth than Neptune, is truly bizarre. It's orbiting in the Kuiper Belt, a donut-shaped ring of ice objects circling the Sun. Haumea has 2 moons, a weirdly elongated shape, and a day that lasts 4 Earth hours. But the coolest thing, the dwarf planet is surrounded by incredibly thin rings. They're likely the result of an ancient collision. It takes Neptune almost 165 Earth years to make one full orbit around the Sun. In other words, since the gas giant was discovered in 1846, it's only circled the Sun once. Okay, so let's assume this teeny-weeny grain of sand, just about 0.1 inches in diameter, is our home planet Earth. Trust me, we're not even that big on a cosmic scale, so I'm flattering us a lot. You'll see. Anyway, the moon will be just about here, a little over 2 inches away, and we'll have to find a grain of sand that's 3 times smaller than the first one. It's hard to say if this is the one, so let's again assume it is. Now, what's the closest neighbor to Earth apart from the moon? That's right, Venus. It's called our sister planet because it's roughly the same size and mass. So this here grain of sand is gonna be it. As for the distance, we'll have to take a little walk now. And there we go, over 20 feet away from the grain that is the Earth. And that's at its closest, mind you. Next comes Mercury, and it's more than twice as small as the Earth. So let's take a grain of salt this time for variety. How far do you think it is from its neighbor, Venus? Not even close. It's here, almost 26 feet away. If you've ever seen a London double-decker bus, it's just short of that vehicle's length. Okay, Mercury is the closest planet to the Sun, so naturally, here goes. The big and mighty star, measuring as huge as this rock. It's roughly 8 inches in diameter. So it fits. Now, where should I place it? Well, you'd better take another double-decker, and then some, because the Sun's distance from Mercury is 30 feet, even further than Venus. And a walk from here to Earth is quite a trip already. All in all, the distance is just short of that between 2 baseball bases. Cool, huh? But we've only just begun. Moving away from the Sun, next comes Mars, which is twice as small as the Earth. Let it be a red pepper grain this time. The distance to it, though, is even greater than from Mercury to the Sun, over 33 feet. So, we'll place it here. And now, prepare for the real thing. We're crossing the asteroid belt to reach Jupiter. To do that, we'll need to travel about 275 feet. That's almost the height of the Statue of Liberty. And the planet itself is about the size of this grape, just shy of 1 inch. Now, let's take a smaller grape and fly another 330 feet. That's how far Saturn is from Jupiter. Can you still see our rock? Sun, from here? I don't think I can. Now, if you take the Golden Gate Bridge in California and decide to rise from its lowest to highest point, that would be the distance from Saturn to Uranus, the 7th planet in the solar system. Notice how distances grow larger every time? That's far from over, though. Meet Neptune, Uranus's brother planet. Although they're neighbors, it'll take us another 820 feet to get to it. Put 5 Olympic-sized pools in a line, and you'll get the scale. The former Planet 9, Pluto, is our next destination. If we go straight from the Sun, it'll be yet another 4 Olympic pools away, and the size of it is only a speck of ground pepper. Pluto is 6 times smaller than the Earth. And now comes the barely imaginable. Let's first go back to our Sun and start the journey from there. Remember how far that is? Right, more than a half a mile away now. To get to the inner boundary of the solar system from this point, we'll have to travel around the whole planet 4 times. Yep, we're still on the scale where the Sun is just an 8-inch rock. And when it's done, we'll find ourselves in a humongous belt of floating chunks of ice, the Oort cloud. The width of this belt is way beyond our planet's limits, but we'll try. Let's take 3 rocks of the same size as our Sun here and lay them in a line. And now, imagine each of these rocks is the size of the real Sun. That's the width of the Oort cloud for you, which goes in a circle around the whole solar system. If we put it to our initial scale, the Sun won't be even visible, no bigger than an atom. So let's scrap it now and start over, shall we? Okay, now this ring of stones contains within it the unfathomable volume of space. Its radius is roughly 1 light year, or 0.4 inches now, and that would be our ground zero for all the following discoveries. The closest star system from here is Alpha Centauri, and it will be about 1.5 inches away. It consists of 3 stars and at least 1 planet that could be inhabitable. The system is too small to see on this scale, but we'll pretend this grain of sand is adequate and proceed further. Next, we go to the edge of the Milky Way galaxy, our home. The galaxy itself is about 100,000 light years across, but we're not far from its very center, so the journey will only take us 50,000 light years. On the super shrunken scale we've created here, it will be 1,650 feet. If you lay down the CN Tower in Toronto, it'll only be a few dozen feet longer. From here, the nearest galaxy to us is the Andromeda. In some distant future, it'll collide with the Milky Way. But right now, to get there, we'll need to travel nearly 15 miles. That's 2.5 million light years in normal count. If you're interested, it's also 2.5 depths of the deepest point in the Mariana Trench, known as the Challenger Deep. Next up is an object we could finally place on a larger scale, NGC 604, a star nebula located in the Triangulum galaxy. If it were in a single line, we'd only need to travel 1.2 miles from where we are now, so let's do it. And the nebula itself is about 1,500 light years in diameter, which is equivalent to 50 feet. That's like a 5-story building. But let's get back about half a mile and look at something else. This object is almost exactly the size of a Boeing 747, and surprisingly, it's a galaxy. A dwarf galaxy, to be precise. Messier 32 is 6,500 light years across and is a satellite to the Andromeda galaxy. They move together, Messier being tugged along by the gravity of its big sister. And now, I'm going to take you for a ride of your life. Get ready, we're going into distances and sizes that would seem impossible if they weren't true. Let's first get back to the circle of rocks that is our solar system. Moving up and away from our star system, we can see the Milky Way galaxy, spanning 0.6 miles wide. Shooting upward still, we see the great emptiness around the galaxy that we've already crossed today. 15 miles of nothingness. Then, we see the galaxies and dwarf galaxies surrounding ours. First, the Andromeda, then others, until we're high enough to see the whole local group. It's a galactic cluster in which the Milky Way is no more than 1%. The diameter is 62 miles. But higher still we rise, and now we're looking at a bright and shiny Laniakea supercluster, which is home to the local group. From here, our galaxy isn't even visible. The diameter of the supercluster is about 3,200 miles. It's more than the distance from Los Angeles to New York. And even that's not all. Higher and higher until we see the boss Great Wall. It's a supercluster located unimaginably far from us. And on our current scale, its diameter is about 6,200 miles. That's longer than the Great Wall of China, with all of its branches. No wonder it's the boss. And finally, we're up in outer space now. Even though the model of our whole galaxy stayed so far below, you can't see it without a telescope. And we're now looking at the largest object in the observable universe, the Hercules Corona Borealis Great Wall. On the current scale, it's as far as 62,100 miles away from Earth, or a quarter of the distance to the Moon. And its diameter is the same, so it takes up another quarter of the way. There are trillions upon trillions of galaxies, nebulas, and stars, and nearly infinite possibilities out there. And yet, the universe is always expanding, so it's also only the beginning.
So check this out. Astronomers have discovered an exoplanet they're calling Super Saturn. It's got rings over an AU wide. An AU is the astronomical unit, the distance between the Sun to the Earth. That's an incredibly huge ring system, hence its name. Super Saturn is being called Mamajek's object after the astronomer who led the team to whom we owe the discovery. Professor Eric Mamajek of Rochester University in New York found Super Saturn while scouring through data downloaded from wide-angle transit observations. WASP is the acronym for Wide Angle Search for Exoplanets. It's an ingenious project developed in the year 2000 by astronomers at Queen's University in Belfast, Northern Ireland, and St Andrews University in Scotland. Using 4 telescopes, the CCD video cameras on the scopes record the slight dimming of starlight caused by objects passing in front of stars. This is called the transit method of exoplanet detection. So, for example, the planet Venus transits across our view of the Sun every couple hundred years. A black dot, the silhouette of Venus, is visible, crossing in front of the Sun as Venus passes between our line of sight and the Sun. This tiny eclipse causes the amount of sunlight coming to Earth to be reduced by a minuscule amount, also known as teeny tiny. The same is true for all the stars in the Milky Way that have planets going around them. Exoplanetary transits in front of stars must be in direct line of sight with Earth for the starlight to be dimmed. Such transits do not occur very often. That's why thousands of stars must be looked at simultaneously for as long of a duration as possible, between 4 and 8 hours a night. WASP was created to stare continuously at as wide of a range of stars as possible. Maybe one of them would show an exoplanet transit. That translates into a lot of data being produced, about 40 gigabytes per viewing session. Computer scientists at Leicester University in England developed a computer program to store the data and generate photometric graphs of the light intensity of each star. Open University, also in England, joined the WASP project, took this data, and made it available for research by astronomers worldwide. The graphs of the intensity of starlight show that changes in its brightness are called light curves. These graphs have 2 axes. One is in the timeline axis, the other one is the intensity of light. As the object, considered an exoplanet, though it could also be a brown dwarf star, crosses in front of the star, the timeline axis keeps track of how swiftly it is moving. It tells us how close the object is to the star, while the brightness axis keeps track of how much the starlight dims. This way, we can find out how large the object is. Now, obviously, big objects will dim the light more and be easier to detect. At present, Earth-based equipment is not sensitive enough to measure the dimming caused by planets as small as Earth. Neptune's size and larger ones are the limit for WASP. However, the James Webb Space Telescope, which is now in operation, has a much greater sensitivity and will be able to resolve the transits of Earth-sized exoplanets. Now, I know you want me to get to Super Saturn, but there's something else you should be familiar with before we get there. If the exoplanet has an atmosphere, or, in the case of Super Saturn, a ring system, the starlight from the star the planet is transiting will shine through the atmosphere or ring system, and that can be detected too. The light curve will show less dimming in the photometric data, because not all the starlight is being blocked. Some light is still getting through the atmosphere or rings. This is important because it gives astronomers a reading of the atmosphere. The James Webb Space Telescope is fitted with spectroscopes that can determine the gas content of the transiting exoplanet atmospheres: oxygen, methane, carbon, etc. The WASP project has been really catching on. There's a Super WASP project now consisting of WASP North and a WASP South. One looks at the sky above the northern hemisphere, the other looks at the sky above the southern hemisphere. There's also a Next Generation Transit Survey, NGTS, based on the WASP project. It's automated, so astronomers don't have to stay up all night sipping coffee, but they can if they want to. Located at the European Southern Observatory in the Atacama Desert in Chile, the NGTS scans millions of stars and has discovered over 100 exoplanets, down to a size as small as 3 times the size of Earth. NGTS has started a Planet Hunters Club on social media. Citizen scientists can search the online database of light curves and perhaps discover your very own exoplanet. What had been a strictly British effort started by 1 or 2 astronomers is now a worldwide phenomenon. With the ability to read the spectroscopic signatures of atmospheric gases during exoplanet transits, a new idea emerged: techno-signatures. That is, specifically identifying gases in exoplanet atmospheres that are produced by civilizations. The James Webb Space Telescope can do this. Gases from pollution, such as chlorofluorocarbons (CFCs), can be seen spectroscopically if present. Tritium from fusion reactions, if they have them, can also be detected, along with heat patterns from cities on the planet's surfaces. Technosignatures is a recent concept that originated after the WASP project started. Who knows what it will turn up? Now, let's get back to Super Saturn. The star that Super Saturn orbits is J1407, a small, dim, sun-like pre-main sequence star of the 13th magnitude. Huh? Well, the human eye can only see stars to about the 6th magnitude, and each magnitude is 2.5 times dimmer than the previous one. So, it's not an exceptional star, just another telescopic star out there in the Scorpius-Centaur region of the night sky. J1407 is a young star that hasn't yet settled into its stable, long-duration phase. This is important because Super Saturn, officially J1407b, is showing signs of having a ring system in an early stage of development. Super Saturn's light curve was tucked away in the mountain of data from the Super WASP project. Professor Eric Mamajek and his associate Matthew Kenworthy of Leicester University studied the data thoroughly and produced a detailed report on it. Knowledge depends on good data. The horizontal axis of J1407b's light curve, the time axis, is what's causing all the hubbub. It took Super Saturn weeks to transit across in front of its parent star, 56 days to be exact. Planetary ring systems that we are familiar with in our solar system orbit right around the equators of the gas giant planets and are very thin, from only a few meters thick down to a few centimeters. In a telescope, Saturn's rings will seem to disappear when the planet is at 0 inclination toward Earth. Saturn must be inclined at an angle in relation to Earth to see Saturn's beautiful ring system. It's something everyone should make a point of seeing: Saturn in a telescope. If Super Saturn's rings blocked most of the light from J1407 for 56 days, It means that the planet had to be orbiting at a steep inclination to its star. If it were at zero inclination, we wouldn't see the rings blocking any light. Therefore, the orbital time could be determined 10 years minimum to 200 years if the orbit is highly elliptical. The superplanet itself is calculated to be 24 times the mass of Jupiter, which means that if it is gaseous, it could be a brown dwarf star. Super Saturn appears to have a Mars-sized object orbiting around it, because there is a huge gap in the rings that was most probably cleared out by a large object. The Cassini division in the rings of Saturn is where the moon Mimas has cleared out a path through Saturn's rings. The light curve of Super Saturn has only been observed once. All the exoplanet detection systems are keeping an eye out for it to come back around J1407. No one knows when that will occur. Some astronomers have suggested that J1407b is a brown dwarf star system in itself, merely passing in front of, but not connected to, star J1407. An orbital reappearance of Super Saturn would disprove that conjecture. The center region of Super Saturn blocked out all the light from its primary star. This is what indicates that the ring system is new and in an early developmental phase. Over time, the very dense ring mass close to the planet is expected to thin as all this matter gets absorbed into the planet or ejected into space. This is what has happened with our solar system's gas giant planets. The Mamajek object is a shocker. Never before or since has a light curve been detected like Super Saturn's. Super Saturn has added a new chapter to our understanding of the formation of ring systems. So, here's to you, Super Saturn. Hope to see you again soon. Imagine a being so powerful it can suck in entire galaxies, so mysterious it's invisible to the naked eye, and so impressive it bends the very fabric of space and time to its will. Yes, meet my mother. Just kidding. Actually, meet the ultimate superhero of the universe, the black hole star. What is it and how does it work? Well, let's find out. The universe is full of marvels, and the black hole star is one of the most impressive ones. It's a supermassive force that can bend the laws of physics, and a true enigma for scientists to unravel. No wonder science fiction writers find them so captivating. A black hole star, also known as a quasi-star, is a hypothetical type of extremely massive and luminous star that may have existed early in the history of the galaxy. They're predicted to be as luminous as a small galaxy, but unlike modern stars, they weren't powered by nuclear fusion in their cores. A quasi-star's energy would come from material falling into a black hole at its core. And yes, just like a normal black hole, these stars have the power to suck in anything and everything that gets too close, including stars, dust, and even entire galaxies. But how is it possible that the star is born from a black hole? And what's more, how do they continue to coexist together? Well, first let's discuss how black holes are born in general. It all starts with a supermassive star, one that is at least a few times more massive than our own sun. This giant of a star burns bright and hot, shining with the light of a million suns. But eventually, it runs out of fuel and its fate is sealed. As its lifespan comes to an end, it makes one final massive boom, a blast so powerful it can outshine an entire galaxy. This blast is called supernova. During this boom, the outer layers of the star fly away, while the core gets squished together by its own gravity. If the squished core is heavy enough, it can keep squishing until it becomes a black hole. And just like that, a black hole is born. Don't even try to put diapers on this thing. Now, this cosmic monster baby can continue to grow by swallowing up anything that comes too close, including stars, dust, and even entire galaxies. This is basically what's happening now in our universe with supermassive stars. But what about quasi-stars? The formation of a quasi-star could only happen early in the development of the universe, before hydrogen and helium were contaminated by heavier elements. And because of that, quasi-stars have one important feature. They are gigantic, so enormous that it's literally impossible to imagine. They may have been dwarfing even the largest known modern stars, like VY Canis Majoris and Stephenson 218. No wonder they're so scary. They were born from protostars, one of the first stars in the universe, the great-great-grandfathers of, everything. So now imagine a protostar so massive that its core collapses into a black hole, just like we described before. But the key difference is that in a regular supernova, the outer layers of the star are blown away by the energy released during the boom. Meanwhile, in a quasi-star, these outer layers are massive enough to absorb the energy without being blown away. What do we get in the end? A star with a black hole in its core that weighs from 1,000 to 10,000 solar masses. This quasi-star is about 14,000 times bigger than our Sun, which makes them bigger than any star we know today. These celestial titans have some pretty crazy properties. Once a black hole is formed at the center of a giant protostar, it starts to give off a ton of energy. This energy helps to balance out the force of gravity, making it kind of a giant fusion-based star. They would be so bright that each one would look like a small galaxy. Quasi-stars would have a pretty short lifespan, around 7 million years. Just for comparison, our Sun is about 4.5 billion years old, and it's only halfway through its lifetime. But either way, during this short period, the black hole at the center would grow to be about 1,000 to 10,000 times the size of our Sun. Quasi-stars are also thought to be super hot, with temperatures reaching over 17,500 degrees. But as a quasi-star gets older, it starts to cool down, and its outer layers become see-through. Eventually, it cools down to a temperature of 6,740 degrees, and at that point, it's curtains for the quasi-star. It can't survive at that temperature, so it just dissipates, leaving behind an intermediate mass black hole. Unfortunately, right now, there's no observational evidence for the existence of quasi-stars. This is because they're thought to have only existed a very, very long time ago. They may have been very massive population 3 stars, which are extremely rare and difficult to detect. It's also very unlikely that any of them would still exist today because of their super short lifespan, only 7 million years. So why do scientists believe that quasi-stars could have existed? Because they're looking for ways to explain how supermassive black holes formed so early in the history of the universe. They're found at the center of most galaxies. But how could these monsters have formed so quickly? After all, it takes a really long time for small black holes to grow into supermassive ones. This is where the idea of quasi-stars come in. These stars aren't just destructive forces of nature. They're like the black belts in the martial art of gravity. They can bend and twist anything to its will. That's why these stars, if they really existed, had to play a crucial role in the evolution of galaxies. They must have been instrumental in shaping the universe as we know it. So, those intermediate-sized black holes that they left behind could eventually turn into supermassive black holes in the center of galaxies. But we're still yet to solve this cosmic mystery. Detection and study of black hole stars is like trying to find a needle in a haystack. Only instead of a needle, it's an invisible and mysterious object. And instead of a haystack, it's the vast expanse of space. But with the help of some pretty cool technology and a lot of brainpower, scientists are getting closer to uncovering the secrets of these celestial giants. Here are some things that can help us in this research. First of all, gravitational waves. They're like ripples in the fabric of space-time, caused by the movement of massive objects. Albert Einstein predicted them way back in the 20th century, but they were finally detected only in 2015. We caught them by observing the collision of 2 black holes. This discovery confirmed that black holes can merge and that they're a powerful source of gravitational waves. Scientists think that by studying these waves, they can learn more about how black holes form and grow. We can also try to detect quasi-stars by observing the effects of their gravity on nearby objects. It's like trying to spot a criminal by their fingerprints. For example, if a black hole is located near a star, scientists can observe the star's light being distorted as it's pulled toward the black hole. And of course, we can use our technologies, such as X-ray, infrared, and radio telescopes. This allows us to study black holes in various ways and at different stages of their lives. In other words, scientists are working hard to uncover the secrets of these celestial giants. We develop new telescopes, search for primordial black holes, and try to understand the connection between black hole stars and dark matter. And we're making some pretty incredible discoveries, just like with gravitational waves. All these things will bring us closer to uncovering the secrets of quasi-stars. And when we find out the truth about them, it will become a new page in our scientific history. So, imagine that ChatGPT will start perceiving itself as a person and will feel emotions in a few years. Many people are afraid that it will want to take over the planet. However, this fact won't be as important as the question people will start asking themselves at that moment. If humanity has created a machine with self-awareness, then could it be that humanity was also created artificially? Now, artificial intelligence lives on the internet, computers, and in digital reality. But what if we also live inside a huge, powerful computer? What if our universe is just a simulation? The most extraordinary thing is that some facts seem to point to this. There's a whole science in the world that studies this theory. It's called information physics, and it assumes that time, space, and matter are not fundamental natural phenomenon, but bits of information. This information forms a picture that creates the laws of physics for us. For example, we feel cold and warm not because atoms get cold or warm, but because their movement accelerates or slows down. The speed of particles can be like bits of information. Billions of them could form the picture of reality. Once, philosopher Nick Bostrom said that an advanced civilization could create such complex technologies that simulations of these technologies would be indistinguishable from our reality. And Elon Musk said in 2016 that we were most likely in a simulation. Wow. The laws of physics resemble a giant code that programmers write when creating apps or games. For many of us, all these complex trigonometric equations and formulas of the laws of physics are too complicated. Tell me about it. But scientists who understand this issue see that the principal workings of these laws are beautiful, and this may suggest that someone deliberately created this beauty. Virtual worlds, apps, or games are based on information processing. If you delve into this information, you'll see that it consists of bits and pixels. Any picture on your phone screen is pixels, and any file transfer process is based on bits. They add up to bytes, kilobytes, megabytes, and so on until a bigger picture is formed. And if our life is a simulation, it must also consist of bits. In our case, pixels and bits are atoms and other particles that make up our universe. There are processes inside your computer and phone with maximum speed limits and computing power. If you start exceeding it, then your device will start working more slowly. So, in our reality, there is also a maximum speed limit. This is the speed of light. When an object starts moving almost as fast as the speed of light, time slows down for that object too. Also, time flows more slowly near a black hole. This object, with an unimaginable gravitational mass, can be something heavy that overloads the processor's computing power. There's also such a thing as quantum entanglement, in which two particles can be connected even though they're far away from each other. Electrons travel around an atom. They are connected, and if the property of one changes, the second one will react. And even if you place these electrons on different sides of a galaxy, they will retain this connection. How is this possible? Scientists don't know. A double-slit experiment is one of the most famous experiments that hint that our world is a simulation. The existence of this experiment can be reduced to a simple thesis that the world exists only when we look at it or interact with it through touch, hearing, and other senses. So imagine that you've launched a new game on an old computer. Sometimes the game map freezes. In the game, you turn to the left and see how the mountains and the roads are getting loaded. Then you turn to the other side and the same thing is happening there. In other words, the world in the game only loads when you look at it through the eyes of your character. This is necessary to facilitate the work of the processor. It's much more efficient to get a piece of information about the world when you look at it than to keep the whole world running simultaneously. Remember this. And now let's move on to the experiment. So, you have a device that fires small balls of light, photons. You release photons from the device and they crash into a blackboard, leaving white traces on the black surface. Now, put a wide plate with a little vertical slit on it between the device and the blackboard and fire photons again. The balls start crashing into the plate, but some of them fly through the thin gap. They smash into the blackboard and leave a vertical white mark on it. Everything looks quite logical, but now cut another slit with the same length and thickness in the plate. You release photons toward the plate. Some of them fly through the two slits. What do you think the trace on the board should look like? Two white vertical stripes, right? Well, take a look at the board. It's covered with many vertical lines. When photons pass through the plate, they acquire the properties of a wave and crash into the board, leaving a strange trail as if they've passed not through 2, but through 10 slits. So, at what point do they change their trajectory? Let's take a look. So, you stand between the board and the plate to see how particles turn into a wave. The device releases photons. They are passing through the two slits. Nothing unusual. There are 2 vertical traces on the board and no waves. You close your eyes and release photons again. This time they behave chaotically and leave many lines on the board. That is, their behavior changes depending on the observer. When you look at them, they behave logically. But when you don't look, the laws of physics seem to stop working. Does it remind you of anything? It's like you're playing a game and looking at the world around you, which is loading. But if you don't look, the world stops working. Scientists still don't have a clear explanation of why particles behave differently when there's no observer. Hey, maybe they're shy. And this is not the only mystery. In the world of quantum physics, many laws of nature don't work. This is a science that gets more questions than answers every year. If we imagine our universe as a large hologram, then quantum physics would be its program code. What if people someday understand this code and learn to change it? This would allow us to transform space, time, and matter. The whole reality could be rewritten. Does the code say that material objects can exceed the speed of light? We would rewrite it and make the speed limit 100 times higher. Does 1 hour last 60 minutes? What if you change one line of code and make 1 second as long as 1 year? A few software changes in the laws of physics would make it possible to turn snow into gold and the ocean into powdered sugar. The whole universe would turn into a vast playground. It seems cool at first glance, but people would probably lose control soon. The universe would be in chaos, and the beauty of our world is in the order that exists here. Now let's go back to artificial intelligence. Suppose its power reaches the level of the human brain, and it will become aware of itself. In that case, it won't come as a shock to it because it will most likely know the history of its appearance and stages. But how will we react if people discover they are a computer program? A computer program is too simple a word. A human is a complex, intelligent, multifunctional organism that experiences emotions, contemplates beauty, has abstract thinking, and much more. The term creation is more appropriate here. It won't matter if we were created artificially because our creation will still be beautiful and complex. Besides, remember that good video games or apps can be made only if developers love their creations. Incredible news has recently spread across the internet. NASA has discovered evidence of a parallel universe. But is this actually the truth? Well, there is a grain of truth in this story, but it's not that simple. Let's consider it. Perhaps you've seen the articles that said NASA has finally found a parallel universe. This story was widely publicized, and people got divided into 2 camps: those who took this news at face value and those who considered it all complete nonsense. But both sides aren't exactly right. Let's start from the beginning. The discovery was made by NASA's ANITA. This name stands for the Antarctic Impulsive Transient Antenna. Yeah, it was designed to study neutrinos. Neutrinos are high-energy cosmic particles. They're incredibly small, lack any charge, and have almost no mass. Trillions of such particles pass through our bodies every second, and we don't even notice them, all because they almost don't affect ordinary matter, That's how insignificant they are. On average, in our entire life, each of us gets affected by a maximum of one neutrino. So basically, hunting neutrinos is like hunting ghosts. To catch them, you would have to send a whole stream of these particles through a giant piece of lead, and it has to be trillions of miles thick. At the same time, you have a 50-50 chance that you'll stop one of them. Therefore, in order to detect them, scientists had to come up with some clever tricks. We know that neutrinos, like other similar particles, come to us from outer space. Ooh. They travel to Earth from the Sun, stars, and even from the Big Bang itself. Some of them come to us from particularly big sources, such as black holes, supernova, pulsars, and even from various unidentified objects. Some of these particles have particularly high energy, and for scientists, these neutrinos are the most interesting ones. But, oddly enough, most high-energy neutrinos don't actually come to us from afar. They form right here, next to Earth. This process has a cute name: particle shower. Well, this is how you can explain it in simple words. A granny particle gets into Earth's atmosphere. Usually it's a particle with very high energy. Then it generates several children that have less energy. Each of them then makes more grandchildren whose energy is even less than theirs, and so on, until we have a giant family tree of low-energy particles. In the end, there may be billions of them. During this process, piles of neutrinos are created. Then they begin to sink deep into our Earth. During their journey through the planet, they touch the upper layers of its crust or ice, for example, Antarctica's ice. When faced with all these obstacles, they create radio pulses, and as you might have guessed, these are the exact radio pulses that scientists are trying to find. It may be a surprise to you, but Antarctica is pretty deserted, you think? And that's why it's the best place to study microscopic particles, which usually can barely be traced. There won't be any interference or anything like that. We can catch these pulses with the help of powerful antennas. NASA places these antennas on balloons that can rise as much as 20 miles above Earth's surface. That's how they've been tracking these neutrinos for the past years. Alright, now we know what ANITA is doing. But what about that parallel universe stuff? Nah, don't worry, we're getting there. In 2018, ANITA began receiving abnormal radio signals that caused quite a stir in the scientific community. Remember how neutrinos come to us from outer space and then gradually sink deep into our planet? So, recently, ANITA has discovered neutrinos that didn't descend from space as usual, but rather rose up from Earth. In other words, these particles, called tau neutrinos, basically travel back in time. But how is this possible? Scientists began to research them. At first, they thought that maybe it was a detector error or an error in interpreting the data. But no, everything was correct. Something very exotic was happening. If so, then first we must try to find a simple explanation. What if these tau neutrinos just came to Antarctica from some other source? Maybe they came to Earth from the other side and somehow passed through the boundary. To test this theory, scientists decided to seek help from another cool neutrino observatory called IceCube. Yes, very cool. This observatory is located near the South Pole. It consists of 5,160 optical detectors buried in ice, and all these powerful detectors are designed to detect neutrinos. ANITA researchers were like, "Hey guys, we found some strange radio signals. Could you please check where they come from?" "No problem," IceCube replied, and started their research. And as a result, they found nothing. Yep, IceCube didn't detect any signal sources at all. It turned out that these strange particles had basically appeared out of nowhere. How could this be? Scientists tested many different theories, but none of them could explain the situation accurately. Later, IceCube published an article which basically said, "Nope, we have no idea where these signals came from and how to explain them in terms of the standard model of the universe." Oh, now it's getting interesting. So, what on earth are these signals? Having exhausted normal explanations, scientists began to consider ideas that go beyond our understanding. One of them said that perhaps these particles had come to us from a parallel universe where time flows in the opposite direction. This crazy-sounding theory is the result of the famous multiverse theory. According to it, about 14 billion years ago, when the Big Bang happened, two twin universes were born. One of them was ours, and the other was a parallel one. And they're almost identical in everything, except for some things. For example, time in this parallel universe doesn't move in the same way as it does in ours. It moves backward. Besides, everything there would look upside down to us, as if we're looking in a mirror. Therefore, scientists call it the antiverse, and believe it could be filled with antimatter. And even though all this may seem strange and crazy to us, for those who live in that antiverse, their way of life would be quite normal. In fact, they would rather find us, the strange ones. So these mysterious neutrinos could be born in this antiverse. Let's say they somehow existed there and then accidentally got into our world, where we were able to detect them. The idea of the multiverse itself is really incredible. If it's true, then it may mean that there is an infinite number of realities, many of which are much better than ours. Quantum mechanics even says that it's quite possible that every second of every day, any of your decisions divides the universe into two. And so there are quintillions of parallel universes where our lives have gone very differently. Something like this is hard to even imagine. Of course, it would be great if we could find a way to get into another universe, and if these mysterious tau neutrino particles were able to cross the boundaries of two worlds, well, maybe we can do that too? But unfortunately, this phenomenon alone isn't enough to say whether the multiverse theory is true or not. This is just one of several possible options. At this stage of human development, we cannot prove or disprove this theory. Maybe someday in the future, we'll find out the truth, but definitely not now. The only thing we can say now, after this discovery, is that we've found strange radio signals which standard physics can't explain. So we need to move in this direction and study them to learn more about this incredible phenomenon. But people like to dream about space, so no wonder we've gotten so excited about this. And it would be great if one day it turned out that this theory was actually true. The theory of parallel universes has been popular in various movies and books for a very long time. Where would you go if you found out that you could travel between realities? Me? I'd look for a different reality of ice cream.
For thousands of years, people knew only about the planets Mercury, Venus, Mars, Jupiter, and Saturn, which they could see using simple telescopes, or even by the naked eye if conditions were good. But in the late 18th century, a famous astronomer named Sir William Herschel discovered a new planet that was icy blue in color. At first, people thought it was a star, but later they realized it was a planet. Today, we know it as Uranus, a planet that's more than 19 times farther away from the Sun than Earth. It's so far away that it takes Uranus 84 years to complete one trip around the Sun. This astronomer also discovered many other interesting things in space, like double stars and nebulae. In the mid-1800s, scientists noticed something pulled Uranus and strangely tugged its orbit. They thought there must be another planet out there, and they used math to predict where it would be. Finally, in 1846, they found Neptune using a telescope. It was too faint to see with the naked eye because it was too far away from the Sun. It was all so exciting. Who knows how many other planets could be there, lurking in the darkness of our solar system? Back in the mid-1800s, astronomers noticed something unusual was happening in the sky. A small rocky planet named Mercury was behaving strangely. It didn't follow the predictable orbit that was expected of it. One of the astronomers was a brilliant French scientist named Urbain Le Verrier. He came up with a theory that there could be another planet in our solar system no one had yet discovered. It would be located somewhere between Mercury and the Sun. This hypothetical planet, which he named Vulcan after the Roman god of fire, would have an incredibly hot surface, and it could be a potential explanation for Mercury's strange behavior. He never surely claimed Vulcan was really the one thing disturbing the orbit of Mercury. But, excited by the possibility of discovering a new planet, astronomers all over the world took the idea of Vulcan. For a planet that didn't exist, people committed to developing ideas and getting information about it. Some scientists didn't think it was likely that they had missed another planet as big as Mercury. It would have been hard not to see it by then. But there was a tiny chance of a smaller planet existing inside Mercury's orbit that was too close to the Sun, so no one could see it. One theory said it was about 13 million miles away from the Sun. Mercury is the planet with the most eccentric orbit in our solar system, but the closest point it gets to the Sun is about 28.5 million miles. This means Vulcan would be under half of that distance. The theory moved on, saying that if Vulcan existed, it would orbit the Sun every 19 days and 18 hours, and its path would be tilted about 12 degrees relative to the path of other planets in our solar system. Vulcan's position at its furthest point from the Sun would still be too close to the Sun to be seen with the naked eye, even during twilight. The only chance of seeing Vulcan would be during a solar eclipse, or when it passed in front of the Sun, which, as the theory said, would be 2 to 4 times a year. They had a theory that this mysterious planet was so close to the Sun that it could only be seen during a total solar eclipse when the moon blocked out the Sun's blinding glare. So, every time there was an eclipse, scientists would peer at the Sun, hoping to catch a glimpse of Vulcan. They were trying really hard, but no matter what, they couldn't find this mysterious planet. Some astronomers claimed to have spotted it during eclipses, but no one could ever confirm or find evidence for that. The theory of Vulcan was left waiting for some better times. Einstein had a different idea. You know about his theory of general relativity, right? That's where he claimed gravity wasn't some sort of natural force, but a result of space-time curved because of the presence of giant space objects, like planets and stars. Planets circle around the Sun in their usual orbit because space-time is curved. That means the planets are kind of falling towards the central star of our solar system. And Einstein tried to explain Mercury's unusual orbit using his own theory of relativity. Unlike the other planets in our solar system, Mercury's orbit wasn't that circular. Instead, it seemed to wobble slightly, as if there was an invisible force pulling it away. Einstein said this could be happening because the massive gravity of our Sun was actually curving the fabric of space-time around it. He claimed it's possible this changed Mercury's orbit a little bit. It took the scientific community a while to test this theory, but it eventually seemed like the most plausible explanation. Even though Einstein's theory gave us a more elegant explanation for Mercury's strange orbit, some scientists were still holding out hope for Vulcan. It was especially hard to let go of the idea of Vulcan because Mercury is also the planet that's really hard to see from where we're standing. But later, more and more scientists started accepting Einstein's theory above their imagination. And they would observe a total solar eclipse specifically to test Einstein's theory of relativity, not because of Vulcan. And Vulcan is not the only hypothetical planet everyone was talking about. In the newer age, some believe there could be a mysterious planet lurking in the outer part of our solar system. But this one is more likely to exist. No one has seen it directly yet, but computer simulations show this so-called Planet 9, or Planet X, is probably somewhere there beyond Neptune. Neptune and Planet X could be similar in size. Planet X could be 10 times more massive than Earth and circles around our Sun in an elongated shape, which is on average 20 times farther from the Sun than Neptune. A year there may last between 10,000 to 20,000 Earth years. By comparison, a year on Neptune lasts 165 Earth years. Something this big moving out there beyond Neptune could explain the unusual orbits of smaller objects in the Kuiper Belt. The Kuiper Belt is the area of our solar system beyond Neptune and where it orbits. And there are most likely many asteroids, comets, and some other smaller bodies there, mostly made of ice. There was another hypothetical planet called Nibiru. Remember those rumors that the world could end back in 2012? One of the popular scenarios was Nibiru, which some claimed would hit our home planet at the end of the year. Of course, nothing happened. We're still here, all set and good, but the idea of Nibiru seemed interesting. Stories started in the 1970s when a man named Zecharia Sitchin mentioned Nibiru in his book, The 12th Planet, claiming it orbits the Sun every 3,600 years. But there's no chance a planet with such an eccentric orbit wouldn't disrupt other planets in our solar system with its gravity. And if it was really coming that close to Earth in 2012, we were supposed to be able to see it with the naked eye. Some simple calculations showed Nibiru would have been nearly as bright as Mars at its dimmest and brighter than the faintest stars you see from a city. Oh well, maybe we'll have more luck in the next 3,500 and something years. In 2011, a comet named Elenin appeared that many people thought could be Nibiru. But when you're looking at comets and planets through a telescope, you see they appear differently. A comet has a coma, which is a gas atmosphere, together with a tail, something a planet doesn't have. Plus, this comet didn't slam into the Earth. It came too close to our Sun and fell apart. The leftover pieces will continue moving on their way to the outer solar system for the next 12,000 years. In a star system far, far away, to be more precise, 2,600 light-years away, there's an exoplanet called Kepler 1658b. It's a gas giant that resembles our Jupiter. But what differentiates it from Jupiter is that this poor planet is doomed. It's spiraling toward its parent star, which will eventually end in a fiery collision. But the most interesting thing? Astronomers would have remained totally ignorant of this fact if not for a tiny clue. It was a really minuscule change in the planet's orbit. It wouldn't have been noticed if astronomers hadn't compared more than a decade of data received by different telescopes. More precisely, scientists have been watching the exo-Jupiter pass between our planet and its parent star once every 2 weeks for the last 13 years. And they've noticed that the orbit of the planet is getting smaller and smaller. Every year, Kepler 1658b needs 131 milliseconds less to complete a lap around its star. If this tendency continues, the planet is bound to collide with its star in 2.5 million years. Even before this discovery, computer models predicted that some planets could meet their end by crashing into their stars. But this is the first time when astronomers have some real proof of such an outcome by measuring almost imperceptible changes in a planet's orbit. They now know for sure what happens when a planet is going to crash into its star, even though we probably won't be around to witness it. But let me tell you a bit more about the doomed planet. It was discovered by NASA's now retired Kepler Space Telescope. It was launched in 2009, and its mission was to find planets orbiting other stars, aka exoplanets. And the very first exoplanet the telescope spotted was the very gas giant we've been talking about. But it took astronomers about a decade to confirm that this space object was indeed an exoplanet. This world is like a denser version of Jupiter. I mean, take 6 Jupiters worth of material, roll it into a ball about 1.1 times as wide, and voila! The planet is tidally locked to its parent star, which means that it makes one complete turn every time it finishes a lap around the star. As a result, the same side of the gas giant is always facing the star. It's the same as what happens to the Moon. Our natural satellite is tidally locked to Earth. That's why we only see half its surface. Now, what is making the exo-Jupiter fall into its star? The same process that is pushing the Moon away from Earth. When a moon orbits a planet, or a planet orbits a star, their gravity forces interact and tug on the other's mass. That's what causes tides on Earth. This tugging releases some energy. It can make an object speed up and slow down. In the first case, a space body will move higher. In the second, it will start moving lower. And this is exactly what's happening to the gas giant. Its parent star is 1.5 times the mass of the Sun. So, no wonder its tidal forces are gradually slowing down the planet's movement, making it fall inward. This all sounds kind of tragic, but this potential collision is by far not the weirdest thing happening in space. Let's look at some others. For example, Betelgeuse, a red giant in the Orion constellation, started to dim in 2019. This confused astronomers. By that time, the star had already swollen to enormous proportions. If it was to replace our Sun, its outer surface would spread far beyond Jupiter's orbit. And then Betelgeuse became dimmer in the fall of 2019. This process continued through February 2020. The changes could be seen with the unaided eye. No wonder, the star's brightness had dipped by 2/3. At that time, astronomers were sure Betelgeuse was about to explode into a supernova. They continued to observe the star, but unexpectedly, it returned to its regular brightness. Thanks to the Hubble Space Telescope, scientists figured out that the star had ejected some of its material, and this partially blocked its light. How about cotton candy exoplanets? Those are particular planets outside of our solar system. Also called super puffs, they have the lowest density ever discovered. This gives them an airy, fluffy appearance. But despite looking like the most popular amusement park treat, such planets are enormous. Come to think of it, scientists often discover strange things in space. Some of them look like blurry blobs. But there's one type of these blobs that doesn't look like any other known space body. The odd radio circles are only visible in radio telescopes. They might be the remains of supernovae, but some astronomers go as far as to claim that they might be the throats of wormholes. Those are hypothetical tunnels between two very distant points in space. The Juno mission noticed something weird in the upper atmosphere of Jupiter. The unusual phenomenon was blue sprites and elves twirling above the planet's surface. These are two kinds of bright flashes of light that appear for short periods of time, mere milliseconds. They extend up and down toward the surface of the planet. On Earth, such flashes usually happen at the height of 60 miles above massive thunderstorms. Rogue planets don't orbit their stars, maybe because they don't have any. These free-floating space bodies travel across the universe and can end up literally anywhere. They're also pretty hard to find. Rogue planets produce only weak emissions, but not so long ago, astronomers spotted the smallest rogue planet in the Milky Way. It's smaller than Earth, but a bit bigger than Mars. Fast radio bursts are blindingly bright bursts of radio waves. They pack as much energy as our Sun produces in days, but last mere milliseconds. Most of these fast radio bursts come from far, far beyond the Milky Way. But recently, astronomers have detected some originating in our home galaxy, and their source is a magnetar just 30,000 light-years away from our planet. If it does exist, nuclear pasta is the strongest material in the entire universe. Formed from the leftovers of extinguished stars, this substance gets squeezed into spaghetti-like tangles of material. It can break, but only if you apply 10 billion times the pressure needed to shatter steel. Not so long ago, scientists discovered that one of the most massive stars in the neighborhood had just disappeared. It was a star 75 million light-years away from Earth. Normally, it'd be too far away for astronomers to clearly see individual stars, but only unless they're huge. And the star we're talking about was enormous. It was shining 2.5 million times brighter than the Sun. For the last time, astronomers saw the star in 2011. They decided to examine it more closely several years later, but it was already too late. The star had vanished. Such massive stars usually go out in extremely bright supernovae, but astronomers noticed nothing like that in this case. There's a theory that the star collapsed into a black hole without triggering a supernova first. It does occur among stars approaching the end of their lives, but very, very rarely. There are black holes, and there might be mini black holes, even though their existence hasn't been proven yet. Unlike their massive siblings, hypothetical mini black holes could be really tiny, not bigger than an atom. Their mass can vary, but just one minuscule thing might have the mass of 1,000 sedans. One theory claims that tons of micro black holes could have been created right after the Big Bang and the beginning of the universe. Some scientists even go as far as to say that a couple of mini black holes pass through our planet every day. More than 7,000 light-years away from Earth, there is the Eagle Nebula, a young cluster of stars just 5.5 million years old. The Hubble Space Telescope managed to take an image of several dark silhouettes near the nebula's center. Those are the so-called pillars of creation, an active star-forming region. Look, how cool is that?
An hour after people disappear, most urban areas will be left empty and quiet. Perhaps the sound of wind, falling leaves, or other natural sounds previously drowned out by city noise and traffic will be heard. The subways of many cities are protected from groundwater by a system of pumps. If there are no people to monitor such systems, most subways will flood within 36 hours. Due to malfunctions, sewage treatment plants will stop working, leading to pollution of rivers and lakes with wastewater. The water pipes in Detroit will become unusable, leading to the flooding of the city. Food in refrigerators will spoil. Raccoons and wolves will inhabit abandoned human homes. Major airports will be covered in rust and overgrown with ivy. Cruise ships in Alaska will sink under the weight of ice that accumulates on them. Lions from the San Diego Zoo will gradually escape, emboldened by the power outage of the electric fence around their enclosures. More and more black cats will appear on the streets of Rome and the Vatican. Rats and mice will consume all edible reserves and leave the cities. Plants will begin to grow in cracks in streets, highways, sidewalks, and buildings. More and more animals will notice the absence of people and flock to the cities. International Space Station will gradually decrease. Since no one will correct its orbit, the station will eventually fall to Earth and burn up. Along with it, digitized samples of human DNA will perish. A large part of the city's territory will be covered with a vegetation of lianas, grasses, and tree seedlings. The Red Square in Moscow will have a layer of soil and thick grasses growing, making the square completely green. Despite high levels of radiation, animal populations are increasing in abandoned areas. Plants have grown in many houses and buildings. Seawater will flood cities that were once drained by artificial drainage systems, such as London and Amsterdam. Satellites will begin to fall to Earth. Since no one maintained their speed of movement, they slowly approached Earth and eventually fell to the planet's surface. Wolves now roam freely around the Brandenburg Gate in Berlin, and wild boars will be seen in Paris. Human speech will be preserved in rare words that parrots have memorized during their years of living with humans. Snakes will not only reproduce at incredible rates, but also grow much larger in size. Their main prey will be rodents that have multiplied in the first years after humans disappeared. Many human-made structures will collapse within 100 years, primarily those with a large number of steel elements. Fruit Christmas cakes, thanks to their alcohol coating, will not only retain their appearance but also freshness. Most buildings will be overtaken by plants and animals, and the city will resemble more of a wild nature landscape. The period of nuclear fuel decay will come to an end, and as a result, dead zones around the ruins of nuclear power plants will once again become habitable. The last parrots that spoke human language may go extinct since they memorized human speech, but it is simply not necessary for their survival in the wild. All modern carriers of information that preserve human culture, laser discs, photographic film, paper, and the like, will turn to dust. Rebar inside concrete buildings, which are more durable than steel ones, will expand 3 times due to rust, causing the destruction of concrete structures. Most modern cities will be covered by a green blanket, and collapsed skyscrapers and buildings will become new hills. Manhattan will return to its former state before human settlement, with numerous streams and lakes. There will be almost no evidence of the existence of human civilization. Only powerful stone buildings that rely solely on the force of gravity will survive, such as Notre Dame de Paris. Of the products that existed during human civilization, only honey, especially in clay pots, and oil in wooden barrels, will be well preserved. Only a few stone structures will survive, including the pyramids in Giza and the Sphinx, almost entirely buried in the sands of the desert, and fragments of the Great Wall of China. By this time, a new ice age will begin on Earth. It is expected that the KEO satellite will enter the atmosphere by this time. Various pieces of space debris will collide with it during its descent, but this will not destroy the satellite. Eventually, it will fall into the waters of the world ocean. Remnants of spacecraft and satellite debris will float through space as the only reminder of human civilization.
The infinite vasts of the universe hold endless possibilities and secrets. And here's one of the intriguing questions: how life and we as humans would look like on other planets. Imagine a world where the laws of physics, the environment, and the conditions are vastly different from what we're used to. How would we adapt and evolve to survive in these strange new lands? Let's see. Mercury is the closest planet to the Sun and has a thin atmosphere. The temperatures there are extreme, with the day side reaching over 800 degrees Fahrenheit and the night side dropping to negative 290 degrees Fahrenheit. So, what can we do to survive these crazy temperatures and constant solar radiation? Maybe we can magically turn into metal. For example, titanium and platinum can perfectly tolerate high temperatures. But seriously though, there is an option. We could settle underground, where the temperatures aren't so frenzied. If we lived underground, we might evolve with large eyes to better capture light. We might also evolve thicker skin to protect ourselves from the intense radiation. Basically, we have two options: become metal or become moles. Let's move on to Venus. This planet is extremely hostile. First of all, Venus is known for its thick, more toxic than your ex type of atmosphere. The whole planet is covered with carbon dioxide, and its surface is absolutely dry, making it incredibly hot. The average temperature is around 847 degrees Fahrenheit, making it one of the hottest planets in our solar system. Also, don't forget about the crazy pressure. Standing on Venus would be like standing 3,000 feet underwater. Only particular hardy microbes from Earth could survive in such conditions. So, if you want to live on Venus, you might have to become a microbe. But unfortunately, since we're not microbes, we have to wear special gear and equipment to survive there. Maybe we'd have to develop a heat-resistant exoskeleton to protect ourselves, as well as get some new lungs that can filter out the toxic elements in the atmosphere. Let's talk about our favorite red sibling, Mars. The first noticeable change after a few hundred years would be your new skeleton. The gravity on Mars is much weaker than on Earth, so your muscles and bones would shrink. To make up for this difference, you'd have to eat more and probably start going to the gym. Also, you'd have to adapt to the low atmospheric pressure and colder temperatures. You need to retain heat, right? That means you need a thicker layer of body fat. Sorry folks, but on Mars, we might become fatter. Another reason to start working out. Another big change would occur in your skin. Your skin is like a big barrier that protects you from harmful things such as bacteria, UV light, looking totally creepy, and so on. So what would happen to it? Most likely, you would turn orange, due to the carotenoids. Carotenoids are a type of nutrient that you get from foods such as carrots, potatoes, tomatoes, and so on. They protect very well against ultraviolet radiation on Mars. They only have one downside. By eating a lot of pumpkins from the Martian farmers market, you'll gradually start to turn orange. But maybe it's not so bad. Maybe life on Jupiter would be easier. Yeah, No, it has no solid land. This planet is made up of hydrogen and helium and is referred to as a gas giant. You would simply float there, like in a huge cloud. And even if you managed to land and tried to walk, it would be like moving through a super thick fog. So how would we evolve there? Firstly, we might become much larger in size to withstand the immense pressures. Secondly, the temperature fluctuations on Jupiter are enormous. The surface is terrifyingly cold and the temperature rises significantly under the outer layers of the atmosphere. Thirdly, if you lived on Jupiter, there would be no verbal language. This gas giant absorbs radio waves, so even if you were speaking, no one would hear you. There would be no music either, so no parties. And what's the point then? Hey, maybe we could communicate with sign language, but that's not so simple either. Jupiter is full of wild winds and storm clouds, so it's unlikely you would be able to see anything. So even if we evolved there in some way, our lives would still not be easy. Before landing on Saturn, you would probably want to check out its iconic rings, but you wouldn't be able to do that because Saturn's rings consist of a bunch of ice particles flying in space, so it would be extremely hard to land. So let's go straight to Saturn itself. At first, it may seem that Saturn is not bad for us. Some layers of this gas giant have quite pleasant temperatures. If we dive deeper into Saturn, it gets surprisingly warm, up to 26 degrees Fahrenheit in its second layer. This is an average temperature in countries like Sweden and Canada. But unfortunately, this is only one such layer. The rest of the planet is incredibly cold, so in order to survive on Saturn, we'd have to do a lot of work. In addition to the cold, we'd have to deal with the planet's harsh environment, including its intense storms, strong winds, and radiation. To protect ourselves from these conditions, we'd need to evolve tough skin, again, find some insulation, and so on. Next planet is Uranus. Uranus has a very different environment from Earth, with much colder temperatures, a lack of a solid surface, and a much different atmosphere. It's like another Jupiter, but with blue vibes. It's not that bad though. There's even water on Uranus. The only problem is, the planet is full of ammonia, that nasty stuff we use for cleaning, so don't be surprised if you feel the gross smell. Also, it's incredibly cold out there, almost like a never-ending winter. So what would it be like to survive in such a dark and harsh environment? We'd need thicker skin, again, to cope with extreme temperatures. And again, we'd need larger eyes to see better in all this darkness. We might even have to develop a new hearing system, like that of dolphins. Wouldn't that be fun? Let's move on to Neptune. If human beings were to evolve on Neptune, they would need to adapt to its harsh conditions. Neptune, the eighth and farthest planet from our Sun, is another gas giant. The only difference is this planet may have a solid core. If we were to live on Neptune, we'd need to float or swim in its methane-rich atmosphere. We'd also need to develop gills or something like that in order to breathe. Basically, we'd turn into space reptiles or cosmic fishes. The gravity on Neptune is slightly stronger than Earth's, but strong winds make it difficult to stand in one place. To withstand the wind, we'd need to be much heavier. Once again, you need to eat a lot and pump up some muscles. Yeah, technically it's not a planet, but we still love it and can't forget it. A small, distant, and incredibly cold world. Pluto's even smaller than our moon, and because of that, there's almost no gravity there. It will be extremely difficult to stand on it. To avoid accidentally flying into outer space while playing football, we need to create a fake gravity machine. And if we don't want to feel dizzy, we need to evolve a brand new nervous system. But Pluto isn't all that bad. For example, there's liquid water under the surface, and even some icy mountains. Maybe it would be possible to survive there if we had some serious equipment, clothes, supplies, and… nah, too much hassle. Anyway, from the scorching heat of Mercury to the freezing temperatures of Neptune, each planet has a unique set of environmental challenges and opportunities for evolution. While we may never truly know what humans would look like on these other worlds, it's exciting to consider the endless possibilities. Never stop looking at the stars and asking these questions.
We've discovered Kepler-22b, a small exoplanet in the Cygnus constellation. Seems like nothing important, right? But it's actually a big deal. This is the first planet located in the habitable zone that was found by the Kepler telescope. In other words, there may be water on this planet. And if there's water, there may be life. Kepler-22b can become our new potential home. So let's take a closer look at it. Actually, discovering new planets is not easy at all. Not all of them can be seen through our super cool telescopes, even the almighty Hubble. Sometimes, the stars are so small and dim that it's really hard to find them on a map. The same thing happened with Kepler-22. In such cases, scientists have to use a special method. First, they take a bunch of photos of the star in different periods of time. Then, they look at them and think, are there any dark dots on this star somewhere? And if they find one, that might be a planet. These photos actually help us to discover some very important stuff. Like, first of all, this planet exists. Secondly, here is its size, radius, and proximity to the star. And finally, will we be able to live there? Now we know that Kepler-22b is very similar to our planet and could potentially become a second Earth. It's also very close to us, only 635 light-years away. Yeah, it's about 3 quadrillion miles, but this is one of the closest options. Kepler-22, the star of Kepler-22b, is a yellow dwarf. It's very, very similar to our Sun. The same size, the same radius, even the age is almost the same, 4 billion years. The difference is only in luminosity. It's about 20% dimmer than the Sun. So, no matter how much you strain your eyes, you won't see this star in the night sky. The planet Kepler-22b is about 2.4 times larger than our Earth, and that's pretty good. More radius means more potential water and space to live. Although going from one city to another would take a while. It's scary to even imagine a 3-day-long plane flight. We don't know the exact mass of this planet, but scientists think it's bigger than Earth's. Actually, the mass of Kepler-22b can be up to 36 times greater than that of our planet. What does it mean? Vigorous gravity. If the planet is 36 times heavier than Earth, then gravity there will be about 6 times stronger. Can you barely lift 20 pounds of potatoes? Try 120. Not to mention that you yourself can become much heavier on that planet. You'll have to get incredibly pumped up just to walk there. You have to literally turn yourself into a bodybuilder just to get to work. The worst thing is that with such gravity, it'd be incredibly difficult for plants to survive there. They'd need at least a little freedom to rise up from the ground. And animals. Our dogs and cats would have to turn into little balls of muscle to survive there. But if this planet has its own animals or other inhabitants, we can roughly imagine what they may look like. They probably have a lot of legs to make moving easier. They aren't really tall, but they're very massive and extremely strong. Muscular giant spiders? Could be worse, I guess. The good news is that this is all unconfirmed information. If we're very lucky, and gravity there turns out to be just a bit stronger than Earth's, then, of course, it'll be much easier to live there. The next thing we know about Kepler-22b is that it's about 15% closer to its star than we are to the Sun. If Kepler-22b existed in our solar system, it would be located somewhere between Earth and Venus. Does that mean we're all going to burn? No, silly. As I mentioned before, the star Kepler-22 is pretty cold, just some 10,000 degrees Fahrenheit. And that's why we can assume that the temperatures on Kepler-22b will be about the same as we have on Earth. If the planet orbits its star the same way Earth orbits the Sun, which we don't actually know, Kepler-22b can rotate around its star on its side, like, for example, Uranus. What? Didn't you know Uranus is actually lying on its side? Also, look at its rings. Yes, Uranus also has rings, like Saturn, but they're vertical. The universe is truly a mysterious place. So, if Kepler-22b is really something like that, then the weather on the planet will be, to put it mildly, not very good. Incredibly cold winters will be regularly followed by hot summers. And, just like with tidally locked planets, we'd be able to live more or less comfortably only on the narrow piece of land between these two crazy sides. Let's hope that this is not the case and the planet rotates normally. But it's not all that bad. Studies show that there may be an ocean on Kepler-22b. You already know that water means life, but in this case, it's also a big plus because a planet covered by an ocean always has more stable temperatures. The water absorbs some of the heat and distributes it evenly across the planet. The hot parts cool down, and the icy ones warm up. By the way, that's exactly what happened to Earth billions of years ago. When our planet started getting its first little puddles, our beloved moon helped these puddles to spread all over the planet. Thanks to this, a burning horror that used to be our Earth turned into a cute little ball full of life. So, if Kepler-22b has water but no atmosphere, scientists think that the average temperature there could be around 12 degrees Fahrenheit. But if there's also an Earth-like atmosphere, then the temperature can reach 72 degrees Fahrenheit. That would be nice. And finally, 1 year there is equal to 290 Earth days, about 9 months. The planet has no natural satellites, so unfortunately, we'd have to say goodbye to a beautiful view of the moon. On the bright side, we'd probably be able to see the sun as a distant little star. We could admire it in the night sky, remembering our home, while not hiding from giant spiders. And this is all that we know at the moment. Unfortunately, it's quite difficult to explore such planets, so there's a lot of very important data that we don't know. For example, what kind of planet is this anyway? Yep, we're missing the most important information about Kepler-22b. We don't know if it's a rocky planet or not. And if not, then all the previously mentioned information means nothing. It may turn out to be a gas planet, or a planet covered with gas but with a solid core, like Neptune, or a water world covered with a giant ocean. In this case, it better be a water planet. Then at least we could build some kind of underwater city there. We could filter the water and eat fish, until we evolve into an amphibious species. Does it even count as evolution if we go back to our roots? Scientists, however, think that Kepler-22b may turn out to be a Neptune-like planet. Some astronomers have even assigned the planet to a category of mini-Neptunes. Yes, this is a real planetary category. But this hasn't been proven yet. But even if, fortunately for us, Kepler-22b turns out to be a rocky planet, we still don't know what the atmosphere is like there. Does it exist at all? What if it turns out to be something like the atmosphere of Venus, which is more toxic than your ex? Then we'd have to dig deep underground to somehow survive on this planet. And then we'd have to come up with a heat source, because it's pretty cold underground. Yeah, let's hope this won't be the case. There are many possibilities with Kepler-22b. So far, we don't have a clear answer. But let's hope that scientists will find it before we load the first people into shuttles and send them to conquer Kepler-22b. That would be awkward if it turns out to be a gas planet, or something like that. I hope you feel well rested, because I've got a tough task for you. Don't worry, it's fun. You're going to visit different planets of our solar system and try to run on each of them. Let's figure out where you can run the fastest and where you can barely walk. The fastest man on Earth, Usain Bolt, can run with an average speed of about 23 miles per hour, but his top speed is higher, up to 27 miles per hour. Sadly, we can't all be Usain Bolts. The average person runs at a speed of 6 to 8 miles per hour. But maybe there's a planet out there where you can beat the famous Jamaican sprinters' records. But first things first, what will affect your speed when you run on other planets? For one thing, gravity. Depending on how strong it is on the planet you visit, it'll influence your weight. And in most cases, the heavier you are, the more slowly you run. Plus, on all other planets in our solar system except Earth, you'll have to wear a bulky spacesuit. Without it, your chances of survival there are non-existent. And don't forget about extreme weather conditions on most planets. It's either freezing cold or boiling hot, or very, and I mean it, windy. Anyway, your amazing journey is about to begin. Buckle your seatbelt. The first planet on your itinerary is Mercury. As you sneak a peek at this world through the window of your spaceship, you notice that the planet looks eerily similar to the good old moon. But just a few moments later, you realize it's just an illusion. All over the surface of Mercury, you see craters left by space rocks. This may make your task of running on this planet way harder. This and your bulky spacesuit. Duh. But you wouldn't survive on Mercury without this protection. The temperatures on the planet are extreme. 800 degrees Fahrenheit during the day and negative 290 degrees Fahrenheit at night. But there's one thing that can work in your favor on this unfriendly planet. Let's say you weigh 155 pounds on Earth. Then on Mercury, you'd weigh around 58 pounds, which means that despite your bulky spacesuit, you can move way faster than you do on Earth. And maybe your speed will even reach 13 miles per hour if you try really hard. The next planet on your itinerary is Venus, also called the Morning Star. While coming closer, you see a world very different from the bluish planet you might have seen in books. Before landing, you have to get through a super dense atmosphere made up of carbon dioxide. And while your spacecraft is descending, you're watching thick clouds of sulfuric acid pass by. Venus is often called Earth's twin because these two planets are of similar size and density. No wonder that on Venus, you weigh almost as much as you do on Earth, 140 pounds. So your weight is a bit smaller here, but don't forget about your spacesuit. And still, because of almost the same conditions on the two planets, you'd be able to run a bit faster than on Earth, at around 8.5 miles per hour. Your first impression of Mars is that it's freezing cold. The average temperature here is about negative 80 degrees Fahrenheit. Even from afar, the planet looks reddish. Once you make your first step on the Martian surface, you understand why. The ground's covered with rusty-colored dust. The same fine dust is floating in the air around you. Wherever you look, you see golden, brown, tan, and even greenish hues. They depend on the minerals that make up the soil. The size of the dust layer varies from area to area, but in most places, it's around 7 feet thick. That can make running much more difficult. On Mars, your weight would be much smaller than on Earth, a mere 58 pounds. This will help you achieve an impressive speed of 12 miles per hour. Aren't you a champ? What's that on the horizon? It looks like a tornado. Is it a dust storm? Then it's time to make a run for it. Dust storms sometimes cover the entire planet, and you can even see the largest ones from Earth. And now you're facing a problem. You see, Jupiter, as well as Saturn, is a gas giant. This means that the largest planet in the solar system, and Jupiter is so large it could swallow 1,300 Earths, doesn't have any solid surface. Well, you'll just have to imagine what your running workout would look like if you could run on Jupiter. This planet has an atmosphere that consists of hydrogen and helium gas. During your descent, you admire thick brown, yellow, red, and white clouds. They make the planet look colorful and beautifully striped. On Jupiter, you'd weigh 390 pounds. You'd have to break a sweat to simply walk there, wearing your clumsy spacesuit. If you could step on the planet's surface, that is. If you tried to run there, your best result would probably be a speed of 1 or 2 miles per hour. To make matters worse, it's extremely windy on Jupiter, with the wind speeds ranging from 200 to 400 miles per hour. Do you see those rings? That's Saturn, another gas giant with no solid surface. This planet's made up of mostly hydrogen and helium, and its temperature and density change the deeper you go. If you decided to leave your spacecraft and step on Saturn's surface, you'd just fall into the planet. But from above, it looks as if Saturn does have a surface. The seemingly solid yellowish-brown sphere is surrounded by several layers of clouds. The visible outer layer is made up of ammonia clouds. Under them, there are hydrosulfide clouds, and the innermost layer is made up of clouds of water. Even though Saturn is a gas giant, your weight wouldn't be very different here, around 165 pounds. That's because the planet's gravity is similar to that of Earth. But because of the conditions on the planet, and your bulky spacesuit, you'd run a bit more slowly there. at a speed of about 4 miles per hour. Before leaving, you admire Saturn's most famous feature: awesome gray, beige, and tan rings. These groups of tiny ringlets are made of chunks of rock and ice. You also spot several of the 53 moons of Saturn. Oh, that's Titan, an icy world bigger than our moon and even Mercury. It's the second largest moon in the solar system. The next planet on your way is a blue-green ball of ice and gas. That's ice giant Uranus. It has this beautiful hue because the light from the sun gets reflected off the planet's surface. Uranus isn't solid. Hit the brakes! If your spacecraft doesn't manage to stop in time, it'll fly through the upper atmosphere and sink into the icy liquid center of the planet. I doubt you'll be able to conduct your running experiment here. So let's just imagine what it'd look like. On Uranus, your weight would be around 138 pounds. And, against all odds, you could actually reach a good speed here, at least 8 miles per hour. If you didn't get caught in a hurricane, of course. Extreme storms occur on the planet in the summer, when Uranus is heated the most. Then, hurricanes can spread for more than 6,000 miles. The furthest planet from the Sun, Neptune, is 4 times the size of Earth, but 17 times as heavy. The blue surface you see when approaching Neptune is actually a layer of swirling gas and permanent clouds. The planet's mantle is made up of water, ammonia, and methane ices. It's the closest thing Neptune has to a surface. And still, there isn't solid ground for you to walk on. So, once again, try to use your imagination. On Neptune, you'd weigh a bit more than you do on Earth, 174 pounds, but your running speed would be just a bit lower than on Earth, around 5 miles per hour. That's the end of your active adventure. Which planet did you like running on the most? Our universe is full of both amazing and terrifying things. You already know about quasars, black holes, dark matter, and so on. But how about the horrors of space that you haven't even heard of? Would you like to visit the most bizarre worlds in the universe? And it's not me who made this list, but NASA themselves. Welcome to the Galaxy of Horrors, NASA's awesome Halloween collection. Please join me on a journey to some planets and tell me which ones you would consider the most horrible. Buckle up! Our first destination is a gas giant called TRES-2b. It's located 750 light-years away from us. If we used a regular spaceship, it would take us about 10 million years to get there. TRES-2b orbits a yellow dwarf, a star similar to our Sun. It also weighs about 1.5 times more than Jupiter. So, what's so special about it? Well, if you're afraid of the dark, you definitely don't want to visit this place. It's the planet of eternal night, the darkest one of all the planets known to us. But it's not that far from its star, so why is that? The thing is, the surface of TRES-2b reflects light even worse than coal does. Because of this, it seems that there's no light at all. If you were flying across the surface of this planet, it would be like walking with a blindfold on your eyes. Oh wait, actually there is some light. An eerie deep red glow surrounds the surface of the planet. This glow is created by the burning atmosphere, which makes TRES-2b a scorching planet. The air there is even hotter than lava. Oh, but if you think that was bad, let me show you the next place of our horror journey. NASA wasn't beating about the bush while nicknaming this one. Now, we're not just talking about one planet, but 3 at once. They're also located quite far away, 2,300 light-years from the Sun. We would have reached them by ship in about 35 million years. All the planets are in the constellation Virgo, and each is extremely light, much lighter than the Earth. These 3 exoplanets are called Poltergeist, Dragger, and Phobator. Cool names, huh? It's because each of these planets is about to become a ghost soon. The thing is, they don't revolve around a star, but around a pulsar. Pulsars are rotating neutron stars with an extremely powerful magnetic field. In simple words, these are the stars that exploded one day. After the explosion, they usually emit such a powerful pulse that it causes the star to rotate at an unimaginable speed. several thousand rotations per second. At the same time, they constantly emit electromagnetic pulses that affect everything around them. So, you've probably already guessed what's happening with our zombie planets. They're slowly, gradually being destroyed under the gigantic influence of radiation. One day, they'll disappear without a trace. Ghost-like planets orbiting an undead star? Yeah, Zombie World is a fitting name. It's also not surprising that scientists nicknamed this pulsar Lich, despite the long official name. Well, at least these guys stick together on their final dance. This planet has a long name, so bear with me. HD 189733b. This gas giant is 65 light-years away from us. It would have taken around 1 million years to get there on a spaceship. This planet is slightly more massive than Jupiter and orbits its star, an orange dwarf, all alone. At first glance, it may seem friendly. A pleasant blue color and curls on the surface. Kind of resembles a summer sky or foam on sea waves, right? Oh, looks are very deceptive, my friend. This planet has a pleasant cobalt blue color due to the hazy blowtorched atmosphere. This atmosphere contains silicates that condense when heated. In other words, the clouds on this planet have rain made of glass. Yes, it rains hot glass shards here. Oh, and if that's not enough, there's a raging wind on the surface, which is moving at a speed of 5,400 miles per hour. Just to compare, the fastest wind on Earth had a speed of 254 miles per hour, about 20 times weaker. And because of this, hundreds of thousands of glass shards rush horizontally across the planet's surface at breakneck speed. I really don't envy anyone who would want to try to land there. By the way, this isn't the only example of strange rains in our universe. For example, it rains molten iron on the planet Dimidium. Or let's take so-called carbon planets. Their existence hasn't yet been proven, but if they do exist, there would be tons of black poisonous clouds, and it would rain pure gasoline and hot liquid asphalt. Oh, and also, raindrops would explode upon touching the surface. Nothing special. The next planet, though, is actually really strange. It didn't just revolve around its star, it lived inside the star. This cosmic miracle is called Koi 55b, or Kepler 70b. This planet is very far away from us, 4,000 light-years. It would take about 70 million years on a spaceship. It's twice as light as Earth and fully rotates around its star in just a couple of hours. A long time ago, it was an ordinary Earth-like planet about the size of Jupiter. It was peacefully and calmly orbiting its red dwarf star, Koi 55. But everything changed about 700 million years ago. Perhaps you've heard that in a couple billion years, our sun will begin to expand into a huge star, absorbing everything in its path. Well, this is the fate of red dwarfs. Sooner or later, they increase, turning into incredibly hot blue giants. The same thing happened with Koi 55. This star began to increase in size and heat up in temperature, gradually turning into a blue-white giant. It was ready to devour its nearest planets. But Koi 55b didn't care about it. When the star reached it, this planet just settled inside. And moreover, after some time, it left its star, simply returning to the new orbit. How was that even possible? Life inside its star turned Koi 55b into a red-hot round stone. It's one of the hottest planets we've discovered so far. The temperature on it reaches 12,000 degrees Fahrenheit. It's hotter than the sun, which is, let me remind you, an actual star. And for some reason, it's still alive and lives as if nothing happened. Unfortunately, sooner or later, the planet will disappear anyway. It's slowly evaporating itself due to the incandescent atmosphere. But still, it somehow managed to survive the journey through the star, which isn't typical for regular planets, to put it mildly. I envy this willpower. However, not all planets are so lucky. Some are gradually being destroyed by their stars, and there is even an entire system among them. This last planet is a sad loner. It's located 870 light-years away from us. The journey by ship to it would take about 25 million years. This planet is about 1.5 times more massive than Jupiter. This is a very sad, dark planet. A doomed gas giant, which is very similar to hot Jupiter, orbits its star all alone. At the same time, it's located so close to its star that its orbital period takes just 1 day. Of course, because of this proximity, the star gradually absorbs WASP-12b. The scorching heat of the star is slowly destroying and devouring the planet's atmosphere. The planet has only around 10 million years left. But what's more interesting, because of this stretching, WASP-12b acquired the shape of an egg. It doesn't even resemble an actual planet anymore. It's also very hot. The surface temperature of the gas giant reaches 4,000 degrees Fahrenheit. Also, a spectrograph of cosmic origin, or COS for short, found that the planet exchanges matter with its star. They're located so close that they give each other part of their chemical elements. This is a common phenomenon in closely spaced binary star systems, but this is the first time scientists have seen this in a star-planet relationship. What a unique system! To be honest, if I was guaranteed complete security, I'd be excited to visit at least some of them. What about you? Please let me know in the comments. Black holes tearing apart enormous stars, pulsars spinning at incredible speeds and emitting powerful beams of energy, colorful nebulae with fireworks of newborn stars, galaxies of every possible color and size. All of these are found within our universe, but it's not infinite. It has a boundary, a literal wall, and beyond that, there's an absolute nothingness. Right now, we're going to make a journey to that wall. But first things first, our universe is like a humongous nesting doll. If you open it up, there's a smaller one inside. It's a galaxy. Inside that is an even smaller doll. That's our solar system. And the smallest doll of all is the Earth. Each of